Good morning, all my dear friends. Okay, let us see how the questions were given in GATE ESE 2021. Okay, right. I'm discussing some of the questions from network theory, digital electronics, signals and systems, okay, electron devices, analog circuits, EMF. Okay, we'll see one by one how they're given asked. Okay, these are the questions given recently. Very simple question from network theory. This question belongs to network theory. They're asking what is the value of current I flowing in the circuit shown in figure. Okay, simple, they given the circuit and they given the options. This belongs to MCQ. Okay, multiple choice questions. One of the question will be correct, right? Here they're asking us to determine I, this I. Okay, how to find this I? If you know this voltage here, V1, suppose this voltage is V1, okay, then this is 5 volts, this is V1, we need to find a current I. How to find current I? Okay, this current I, nothing but this starting voltage minus ending voltage by total resistance. Starting voltage minus ending voltage by total resistance. Resistance is 2 kilo. In order to determine this current I, we should know the value of V1, that's all. Okay, how to find V1? See here, let us assume this voltage with respect to ground. Let us take this node as a reference node. Let us assign ground potential to it. Okay, just apply nodal analysis here. Okay, just apply nodal. Tell me nodal analysis here. If I apply nodal analysis at V1, tell me nodal at V1, this voltage minus this voltage, V1 minus 5 divided by 2k. Okay, similarly V1 by 2k. This current, okay, whatever the element in series ideal current source does not have any significance here. This current always entering nothing but 1 milliampere itself. Okay, minus 1 milli equal to 0. Solve for V1. Solve for V1, that's all, finished. Okay, here this V1 into 1 by 2k plus 1 by 2k is equal to 5 by 2k plus 1 milliampere. Okay, therefore V1 into this is 2k, 1 plus 1 divided by 2k equal to, this is 2.5 kilo in the denominator, when goes to numerator becomes a milli, right? Milli plus 1 milli. This is 3.5 milli. Okay, this is 2 by 2 cancel. This V1 into 1 by kilo nothing but milli itself, right? This is V1 into 1 milli equal to 3.5 milli. Milli cancel. Then what is the value of V1 in this question? We got this V1 as 3.5 volts. V1 we got as 3.5 volts. That's all. They are asking us to determine current I. Okay, then tell me what is I. Okay, this I. Okay, this I equal to V5 minus V1. What is V1 we found out here? V1 we got this as a 3.5 volts. Okay, this I nothing but 1.5 divided by 2k, or this is 0.75 divided by kilo. Kilo denominator and goes to numerator, it becomes milli. That's all. Now choose the correct option from this. Okay, 1.25 milli, 0.75. Okay, answer B is the correct answer. Option B is the correct answer. Simple question asked recently. Okay, let's move on to the next question. See the question here. The current I flowing through 2 ohm resistor is. They are asking what is the current that is flowing in the 2 ohm resistor. Simple, common sense. Okay, no need to put pen on the paper also. We can write the answers directly. Here, this is I. They are asking the 2 ohm resistor. This is a 2 ohm resistor. This is I. Common sense, we can write the answer. Simple. Answer is 0. Why answer is 0? There is no written path for the current to flow. No written path. Okay, there is no written path for the current to flow. No written path. For the current to flow. Okay, there is no written path for the current to flow. That's why there is no closed loop. Then I, what is the value of I? 0. I is 0. Or if you have any doubt, notice here, I can assume this as one node. Any complex network can be assumed as a node. or I can assume this as some node here. Okay, some node I can assume that as a node. Okay, right now here this is one node N1, this is another node N2, and here some current I is flowing across the 2 ohm resistor. And if I consider this node N2, okay, this is the current I2 flow, I is flowing like this, current I, okay, I is flowing like this. There is no return path. Where is the return path here? No return path for the current flow, no closed path, okay, it's open. That's why what is the value of I? I is 0, no return path for the current to flow. Simple answer, very easy question for this in this gate, okay, right. Let's move on to next question. See here, it's a beautiful concept, okay. See the question first. The locus of impedance Z of j omega is of figure A, that's a figure A, is plotted as the omega is varied from 0 to infinity, okay. This is a plot they given. When omega is varied from 0 to infinity, this is the omega equal to 0 point, okay, and this is the omega equal to infinity point, okay. They are asking to calculate some parameters, that's all, okay. When the locus of the impedance Z of j omega of figure A, okay, is varied from 0 to infinity. Impedance varied from 0 to infinity. They have showed the point, this is the omega equal to 0 point. This is the omega equal to infinity point. Okay. Then the values of R1 and R2. R1 and R2. Simple. If you know the impedance information, we can calculate this question. Impedance, just we require the impedance expression of capacitor, that's all. What is the, see here in this circuit actually, if I calculate this impedance here Z, the nothing but R1 plus this R2 parallel with the C2, that's all, some capacitor C. See, I am taking the diagram again. Oh, what is the impedance of this capacitor, tell me? ZC, 1 by j omega C, that's all. If I know this expression, I can solve this question. No need of that locus also, no need of locus, that word. If you know this expression, we can solve this question. See, I am taking a new slide, okay. You notice here, let us discuss this omega 0, this is the omega equal to infinity points. Yes or no? What is the circuit at omega equal to 0? Let us see. What is the circuit at omega equal to infinity? Let us see the circuit at omega equal to 0, similarly at omega equal to infinity. Okay, omega equal to infinity. Okay, here tell me impedance of a capacitor ZC equal to 1 by j omega C. When omega equal to 0, what is the impedance of capacitor? When omega equal to 0, impedance of capacitor, what is this value? 1 by 0, nothing but infinity. What is impedance of an element is infinity, nothing but it acts as a open circuit. Impedance across an element is infinity, nothing but that element acts as a open circuit. Similarly, notice here, here when omega equal to infinity, the impedance of this capacitor at omega equal to infinity equal to 1 by infinity, nothing but 0. Impedance across an element is 0, then that element acts as a short circuit. Okay. Here, if I take this diagram, notice here, at omega equal to infinity, right now, notice here, this capacitor behaves like a short circuit. This capacitor behaves like a short circuit. This is R1, this is R2, right? This is a short. Capacitor behaves like a short. And we know one thing, anything parallel to short, nothing but short circuit. Resistor parallel to short, nothing but short itself. Okay. And this resistor R2 does not have any significance. Therefore, right now, only R1 is coming into the picture here. R1 is coming into the picture. And they given this information, when omega equal to infinity, resistance is 2 kilo ohms. Okay. 2 kilo ohms. This impedance equal to 2 kilo ohms at infinity. This impedance is 2 kilo ohms. Directly we can write, what we can express here, R1. What is the value of R1 here? This R1 equal to 2 kilo ohms. finished. Similarly, here at this frequency, okay, similarly at omega equal to 0, the capacitor behave like a open circuit, right? This is your resistor R1, this is your resistor R2, and this capacitor behaves like a open circuit, right? This is the impedance. And what is the impedance given at omega equal to 0? When omega equal to 0, this impedance is given as 5 in kilo, okay? Therefore, this is nothing but 5 kilo ohms. And right now, this R1, this R2, how they connected to each other both? Right now, R1 and R2 both are connected in series. This R1 and R2 both are connected in series. This is nothing but R1 plus R2. And here R1 equal to 2 kilo ohms. Therefore, can you please tell me what is the value of R2 then? This is 2K plus R2. This is 5K. Then, what is the value of R2 then? What is the value of R2? Equal to 3 kilo ohms. R2 equal to 3 kilo ohms. Can you please answer right now? What is the answer? R1 equal to 1K, sorry. R1 equal to 2K, R2 equal to 3K. Answer? R1 equal to 1K, 2K, R2 equal to 3K. This is the answer. Option D is the right answer for this question. This is also MCQ question. That's all. Simple. No need, nothing. Simple, just required information about the impedance of a capacitor. Okay, impedance of a capacitor. Capacitor impedance is okay. Capacitor acts as a short circuit at omega equal to 0 and open circuit at omega equal to infinity. Okay, sorry. Capacitor acts as a open circuit at omega equal to 0 and acts as short circuit at omega equal to infinity. That information required, enough. Let's move on to next question here. Next question. This question also belongs to network theory. See, the steady state current I of t of the circuit shown in figure A, okay, is shown in figure B. Then the elements, okay, what are the element and its value present in Z? They are asking the element and its value respectively, Z. They are asking about the Z here. Right. Here we are got all these questions from the memory based of the students. They appeared for the exam and they have sent some questions to us. Okay, right. Maybe question may be sometimes incomplete. Okay, the element and its value means they are asking about Z. Okay, the official question paper from the GATE has to be, okay, it will be out maybe in a week or couple of weeks. Okay, based on the memory based questions sent by the students, we have framed all these things for the purpose of future batches. Okay, for the students who are appearing in future, they should know, who are eager to know how the GATE was. My remark on GATE question paper this year ECE, it's like moderate or little bit difficult, that's all. Some questions, rest of the questions very easy only. Okay, right. Here the steady state current I of t of the circuit of figure A is shown in figure B. Then the element what is present in Z. They are simple, that's the thing they ask. And if you observe here, what is the source given? Sin t. Okay, magnitude is 1. Okay, and directly here we can derive something like the source given as sin t. Sin t. Usually sin omega t, right? Sin omega t. What is the value of omega? When you compare with sin omega t, okay, omega equal to 1 here. Yes, omega equal to 1 radian per second for this question. Omega equal to 1 radian per second. Okay, and here amplitude is 1 here. And if you observe this current, see the current diagram. This current, this is I of t. They given this. This is a, okay, the steady state current I of t of this figure. They given like this. Okay, and they given something here. This current is not passing through origin. It is passing through pi by 4 or 45 degrees. 45 degrees. Okay, it is not passing through origin. It is passing through 45. Okay, 45 degrees. Okay, and this is the origin. When you compare here, okay, right now if I plot my input waveform, this is the input waveform origin, it's a sine t, it's a sine function, okay. Both the frequencies are same. This I of t, V of t, okay. This V of t. What is V of t given? V of t is given as 1 sine t. 1 sine t, okay. And here starts at origin. When compare these two waveforms, this is delayed, okay, delayed. And this waveform, this I of t, okay, magnitude given as 1 by root 2 plus 1 by root 2 minus 1 by root 2. This also sine waveform, okay, advanced, it's a delayed. This is 1 by root 2 sine of, delayed by what amount here? Here omega equal to 1, for this one omega equal to 1t minus that pi by 4. Pi by 4 nothing but 45 degrees itself, radians, okay, or 1 by root 2, this is the sine of t minus 45 degrees. This is the I of t waveform given, okay, right. They are asking us, based on this information of current and voltage, we need to identify that impedance or that element. What is that element? Which type of element? Whether resistor, inductor, okay, or if so, what is the value? Here, if I assume this as some Z equivalent, suppose impedance seen by the source. If I know the information about this voltage, if this current, then ratio of voltage to current will give the impedance. I am talking about impedance phasor, okay. If I know this voltage, this current, okay, ratio of voltage to current will give the information about the impedance seen by the source. And if I write this phasors, V of t given as 1 sine t. If I convert into phasor domain, polar form, this can be written as RMS value at an angle phase. What is the phase here? 0 degrees. And for this 1 by root 2 sine t minus 45 degrees, if I convert into RMS, maximum value, okay, divided by root 2 at an angle minus 45 degrees. Okay, here this root 2 getting cancelled, okay. Here this root 2 getting cancelled. What is the information we got here? This is by 1 by root 2 at denominator, when goes to numerator becomes root 2. Minus 45 denominator becomes plus 45. Okay, this is the equivalent impedance seen from the source, Z equivalent. Equivalent impedance seen from the source. Okay, this is in polar form. Let us convert into rectangular form. Polar form, let us convert into rectangular form. Okay, this can be written as root 2 cos of 45 plus j sine of 45. This is root 2 into, this value is 1 by root 2 plus j 1 by root 2. Root 2 getting cancelled, okay. Then what is the Z equivalent here? This is Z equivalent. Z equivalent, root 2 cancel, 1 plus j 1. That's a 1 plus j1. Here this is 1 plus j1. Right now this is one element, this is another element, both are connected in series. Actually this element, impedance, if you notice here, this is nothing but 1 plus z itself, the Z equivalent here. For this one, if I notice the Z equivalent here, that is nothing but 1 plus z itself. Okay, now tell me 1 plus j1 is a Z equivalent. From seeing the network, this also equal to 1 plus z. Okay, this also Z equivalent. Tell me, therefore Z equivalent equating both the things here, 1 plus j1, okay, equal to 1 plus z, or 1 cancel, Z equal to j1. Here if you observe here, this is the impedance in, okay, Z, impedance of this element Z, that element Z, that's the impedance, okay. And see here, this seems like a j omega L or minus j by omega C. How it seems like a, if I substitute that values, it seems like j omega L, not seems like a minus j by omega C. Therefore, element should be inductor, okay. And given a source is working at 1 radian per second, okay, source is at 1 radian per second. Therefore, equate this omega equal to 1, then L equal to 1 Henry. That's the answer. Okay. Therefore, for the given circuit, what is the value of B? 1 radian per second is 1 Henry is the right answer. Okay. That's all. It's a multiple choice question only, MCQ. Okay. Next question. Notice this question here. For the linear network shown in figure, okay, of figure A, R is variable, okay, and R is variable here, and its characteristics is shown in figure B. This is the characteristics shown in figure B. Okay, right, right. If R is replaced by, okay, if this entire resistor is replaced by this network, okay, shown in figure C, then the value of current I2. What is the current I2? They're telling. That's all. This is the thing here. Simple. For the linear network shown in figure, okay, for this two-port network, okay, this is the characteristics of the R, means a relation between this V2, I2 is flowing here, they given I2, okay, okay, this is V2, this is I2, okay. Right now they given the characteristics V2 and this I2 in this direction, they given this characteristic V2 minus I2, they given the characteristics. Right now what they asking us, when this entire network, okay, this resistor network replaced by 1K and 10 volts in series across the AB terminals, what is the I2 flowing in the network? Okay, what is the I2 flowing in the network? Okay. Right now how to approach this question? We can do one thing. Let us assume the Thevenin equivalent of this circuit. Since network is a linear two-port network, okay, this entire network can be replaced by its Thevenin equivalent. What is the Thevenin equivalent? VTH series with RTH. VTH series with RTH across the terminals AB. This is VTH here, this is RTH here across the terminals AB. And right now this is terminated by load resistance R. Okay, and what is the voltage? What is the current here? This is the voltage V2 given, this is the current I2 given here. Okay, first thing what we will do is, let us try to replace this entire network by its Thevenin equivalent. Okay, then later replace this R by its this network across the terminals AB. Then find the I. Okay, let us come to this network here. From this one, okay, what's the information we can get here? You know, notice here. This is the relation between V2, I2. Notice here, that's a V2, this is I2. And here, if you notice these characteristics, what's the value of IA on the voltage axis? What is the value of I on voltage axis? Here, when I, okay, what is the value of I on the voltage axis? Tell me. I equal to 0. Value of I on the voltage axis is nothing but 0. If current is 0, then network acts as a, here this is nothing but open circuit, no current flowing, nothing but open circuit. Then directly it is giving the information about VOC or VTH for the given network. Right, simple, that's all. VOC or VTH for the given network. See here, we are trying to replace this network by VTH and RTH. Okay, we are trying to find this entire network replaced by VTH comma RTH. Then what is the Thevenin equivalent of this network? VTH series with RTH. Therefore, we found out this VTH from the given graph. Next. Okay, everyone, notice here. Actually, this is a relation between V2 and minus I2. Okay, if see here, this is R like this for this network. This is terminal A, this is terminal B. This is voltage V2 here. Okay, I2 in this direction, this is the I2, or I2 in this direction, nothing but minus I2. Okay, if I know, see here, this information, I am trying to find the RTH here. Directly, common sense, these are the characteristics. This is a V2, this is I2. Just calculate the slope of this one, slope. If you calculate slope, that directly it will give the RTH for the given network. Directly calculate the slope, okay. Here VTH, RTH, okay. Directly calculate the slope between these two, it will directly give the RTH. Height is 1, Okay, width is 4 milli, right? This is nothing but slope. Let us calculate the slope here. This is 5 minus 4, 5 minus 4 width. Okay, this is 0 minus 4 milli directly. Okay, or just magnitudes only I'm talking here. Directly it will give the magnitude. You just take the magnitude directly, slope will give the RTH. Okay, this is 1 by 4 milli. Okay, 1 by 4 milli. What is this value? This is 1 by 4 milli, denominator goes to numerator, becomes kilo, or this is 0.25. That implies RTH for the given network equal to 0.25 kilo ohms. 0.25 kilo ohms. VTH for the given network nothing but 5 volts. Okay, VTH from here, VTH equal to 5 volts. Simple. From the CAT 6, common sense. When this on vertical axis, what is the value of this horizontal value? 0. Okay, this is VI characteristics. Value of current on the voltage axis nothing but 0. Nothing but directly it is giving the open circuit voltage or VTH. Okay, right. Slope, calculate slope, directly it will give the RTH here, right. Therefore, this entire network can be replaced by its Thevenin equivalent. What is the Thevenin equivalent? VTH series with RTH. VTH series with RTH across the terminals AB. Tell me, this VTH, what is the value of VTH here? We got 5 volts. RTH here 0.25 kilo ohms. Okay, and right now terminated by that network here, terminated by, let us terminate by that network. This is 1 kilo ohm, this is 10 volts. Then let us try to find the current I. Tell me there, what is the current I here? Current I2 they asked. Simple, finished. Starting voltage minus ending voltage by total resistance. That's all. This I2 starting at 10, ending at VTH. This expression for I2. This I2 equal to 10, or apply KVL. VTH divided by 1K plus RTH. Or this is 10 minus 5 divided by 1K plus RTH. What's the value of RTH here? 0.25 kilo. This is 5 by 1.25 kilo. Or this is 5 by 4, or 4 times. Kilo denominator, when goes to numerator, becomes milli. That's all. That's the answer. It's nothing but 4 milliamperes. Okay, 4 milliamperes. These are the questions asked from network theory. Okay, simple questions. Okay, basic knowledge, we can solve everything. Okay, let us move on to next thing. Digital electronics. This subject given from, this is a question given from digital electronics. The Boolean expression f equal to x plus y z is equivalent to which of the following expressions they ask you? X plus xy plus xz. Okay, let us see here. Let us take the option A. Let us take everything. Option A, this x plus xy plus xz. If I take these two terms, if I take x as common, 1 plus y, this is xz plus xz. Anything added to 1, nothing but 1 itself, plus xz. Okay, x plus xz, or x if I take common here, this is 1 plus z, this is anything added to 1, again 1 plus something, nothing but 1 itself, or this is x into 1, this is nothing but x. Okay, first expression, it is giving an expression. Okay, if you solve it, you are getting x here. Okay, let us take the second expression here. Second, what is second expression given? X plus y into x plus z. X plus y into x plus z. Let us multiply x into x. X into x nothing but x itself. X into x nothing but x plus xz plus xy plus yz. Okay, Boolean algebra, x into x nothing but x itself. This is xz plus xy plus yz. Okay, this if I take x common here, 1 plus z plus xy plus yz here. Anything added to 1? Nothing but 1 plus xy plus yz. Here this, if I take x common, 1 plus y plus yz. Okay, again this is x plus yz. Second is giving a relation x plus yz. The Boolean expression x y equal to x plus yz equivalent to, they are asking which of the options following expressions. This is a MSQ question. Let us check. Okay, I am taking another thing. Notice here. Similarly, let us take the third expression here. C. Let us check the third expression also. C here. C option. If I take the C option, this is x plus xy plus yz. Common x, if I take here 1 plus y plus yz. Okay, or this is x plus yz. C option is giving a x plus yz. Okay, let us try to simplify. Okay, D option. D. If I take D option, tell me D option D. If I take D, this is xy plus yz. That's all. Or if I take common y, something like xz. From itself here, tell me here which are the expressions related to giving a answer x plus yz. Option A is giving x. Okay, it's not. Option B, okay, if I simplify here, it is giving x plus yz. Option C, if I simplify x plus yz. Option D, okay, some other expression. Then answer here, B and C are the right answer. This is a MSQ question, multiple select questions. There may be more than one correct answer. Maybe more than one correct answer. Maybe all the options are correct, 3 options are correct, 2 options are correct. Okay, you have to. This is the from now in this year onwards, they are introducing MSQ questions, multiple select questions. The right attitude to analyze from the students. Okay, if they want to test this GATE people, they can increase these MSQs and NAT questions, data type questions, fill in the blanks questions. Okay, right way to evaluate the students. Maybe in future you may see more number of MSQs and as well as NAT GATE. Sometimes it may all the question paper may be 0 MCQs maybe in future. Okay, right. The next question, let us move on to the next question. This also came from, by seeing itself, came from digital electronics, multiplexer given. The value of A0, A1, A2, A3 such that output of the multiplexer is XOR. Okay, XOR. And selection lines here, they given C, D. Okay, inputs here I0, I1, I2, I3, 4 by 1 mix. Directly here, this is the S1, S0. Tell me what is the output equation of this multiplexer? Multiplexer output equation. If you write this output equation F for this multiplexer, that selection lines S1 bar, S0 bar into first line like that, right? C bar D bar into A0 plus C bar D into A1 plus C D bar into A2 plus C D into A3. That's all. Okay, this is a general expression. Suppose here from this one we have to test it and see the output. What is the expression for XOR of two gates C and D? XOR of CD. Okay, C bar D plus CD bar. This is an exclusive OR of this one. XOR of two inputs. Okay, C bar D plus CD bar. And if I select the first option, if I choose the first option, if I take this first option, this is 0, 0, 1, 1. Only this is getting CD bar plus CD. This is not XOR. Okay, if I choose the second option, if I choose the second option, 0, 1, 1, 0. Okay, 0, 1, 1. Substitute here. C bar D plus CD bar. Okay, right, finished. Answer is finished. This is a MCQ only, multiple choice question. Okay, if you want to check the other options also, let us check the other options. Okay, here if I take this one, 1, 0, 0, 1, we are getting C bar D bar plus CD. This is giving the output of XOR, but they asked XOR. Okay, this is also wrong option. XOR NOR we are getting the output. Okay, if I take this one, we are getting a different answer. You have to simplify it here. This is C bar D bar, okay, plus this is only the third term, fourth term coming, C D bar plus CD. Okay, this also not on. Okay, XOR gate. Okay, which is giving the XOR output. This one is giving the XOR output. Therefore, option B is the right answer. Option B is the right answer. XOR output. Right. Let us move on to next question. Very good question. Okay. What is the frequency and duty cycle of output? When the input clock frequency is F0 and duty cycle is 25%. What is the information they given here? This input clock is having a frequency F0 and duty cycle is 25%. What is duty cycle? On period by total period, nothing but duty cycle, right? And here they ask you what is the frequency and the duty cycle of the output. What is the frequency and the duty cycle of the output? Here they are asking. Means you need to know the waveform. That's all. This is a given. See here, this is JK flip flop, and see here, this is J, this K connected to the same point, and output of this LSB connected as a input to this JK flip flop. And here this is a 2-bit counter, right? It's a 2-bit counter, 2-bit up counter. Suppose initial state is 0 0. Okay, next state will be up counter means 0 1. Next state will be 1 0. Next state will be 1 1, and the same thing repeats. So and so, same thing repeats. Right? This is the MSB bit. This is the LSB bit. For this counter, this MSB bit, this is LSB bit. Okay, this LSB bit they are connecting to the JK flip flop. Okay, before solving this question, we should know another information about JK flip flop. JK flip flop, what is the truth table of JK flip flop? JK, the next state output Qn plus 1. What is the next state output? When this 0 0, both the inputs are 0 0. Okay, output nothing but here Qn, previous state itself. 0 0, next state nothing but previous state. If I take 0 1, j equal 0, output, this is reset state. Reset means output will be reset to 0. 1 0, okay, output will be set in this one, set to 1. 1 1, if I give 1 1, okay, if I give 1 1, output will be toggle. This is called toggle state or complement state. Toggle. Okay. Okay, and right now we required these two cases. Notice here, which cases we required? If you observe here, when both the inputs are connected to the same thing, 0 0, or both the inputs are connected to the ones. When both are 0 0, you are getting the previous state itself. When both connected to the 1, J1, K1, then toggle of the previous. Okay. For this one, okay, this LSB, right now we have seen this output 0 0, 0 1, 1 0, 1 1, like that again, 0 0, 0 1, 1 0, 1 1, okay, 0 0, so and so. This is the output of the flip flop here, okay, up counter. In this up counter, this is the MSB bit, this is the LSB bit. These LSB bits are given as the input to the JK. Input to the JK here, okay, this is given as input to the JK. JK flip flop. Okay, let us give this set inputs and let us see. Okay, and given one thing, the clock here is a 25% duty cycle. Okay, clock, some clock, let us take some clock here. Let us say take some clock here. Okay, positive edge triggering I am taking here. This is, let us assume this is a clock. Okay, clock. And right now Everyone notice here. Okay, clock given like this. Right now here, let us see the output. Here, when this is 0, let us assume the initial state as 0. Okay, initially, let us assume this as a 0. Initial when this is 0, okay, 0. And we know when 0 is given to jk, 0 given to jk, it's a previous state. It's whatever the previous value, it will be written up to the next clock edge. Next, when this is 1, okay, then this is toggle. Previous state is 0, toggle means it becomes high up to the next state. Toggle. Okay. Next state is 0. Here 0. Okay. Toggle. 0 means, okay, tell me 1 second. 0. 0 means what is the output when jk 1 0 both are zeros? Previous state itself. What are the previous value? It will be written for the next state. Okay, same one itself. Next, when this next state is 1, jk 1, both are 1, next state will be toggle, right? Toggle, previous value toggle up to the next state. Toggle for j1 becomes 0. Next, when again when came back to 0, okay, whatever the previous value, when j0 k0, okay, previous value, it will be retained here like this, 0 itself. So and so it will continue. Next, it will continue like this. Finished. Here itself, let us try to tell from this information, let us try to tell the frequency. So here, this suppose this is t, 1 period, let us consider t0. This is t0 on period, this is off period, this is 25% duty cycle method. Here t0 by 4, actually this is a t0 by 4. From here to here, this is t0 by 4. t0 by 4. On period is t0 by 4. This is 3 t0 by 4. Total nothing but t0. And if you notice this waveform, okay, if this is t0, this is another t0, okay, this is another t0, and here we are getting this as a 2 times of t0 on period. Off period also we are getting another 2 times of t0, and same thing getting repeated. Yes or no? This total cycle, this is 4 t0 we got here. 4 t0. Output waveform, okay, 4 t0. See here, input waveform frequency f0 is nothing but reciprocal of t0. Okay, frequency, this is nothing but 1 by t0. That's the input waveform. Output waveform, for output waveform, tell me what's the frequency here? F output. For output, tell me what is the output frequency here? This is nothing but reciprocal of this one, 1 by 4 t0. Okay, 1 by 4 t0. Here 1 by t0 is f0, then this is nothing but f0 by 4. f0 by 4 is the output frequency. And if you want to answer the duty cycle, tell me here, duty cycle, output duty cycle. Output duty cycle. Tell me output duty cycle here, on period by total period, t on by t total. Okay, this on period is nothing but 2 t0, total period nothing but 4 t0. Okay, this is nothing but 1 by 2. Percentage duty cycle then 50%. 50%. That's all. Finished. Output clock frequency is f0 by 4 and duty cycle is 50%. Everyone, right? Comfortable? Everyone following? Very good. Okay, let us see another question. The gate shown in figure, which of the following is or correct? Okay, you see the answer. When zeros and ones both are available, okay, AND gate cannot be implemented, NOR gate can be implemented, NAND gate can be implemented, OR gate cannot be implemented. This is given in MSQ, multiple select question. Okay, 1 or 2 question, many options can be correct here. This is not MCQ, many questions can be correct. Okay, tell me your answer. What is answer? for multiple selection questions. Multiple select question. Okay, right. Here this gate, by using this gate, see here they given the gate shown in figure. Okay, this gate is nothing but see here this output y, this is nothing but a plus b bar, something like bar is given here. This is a, this is a b bar, a plus b bar is given, right? Okay, let us check what we can implement by using this gate here. What are the things we can implement? Suppose this, for this gate, okay, this is a, this is b, this output nothing but a plus b bar we are getting, a plus b bar. Okay, suppose here itself for this one, if I take this as a 0, if I give this as some a, what is the output I am getting? 0 plus a bar, or this is a bar. I am giving input a, I am getting output a bar, means it is implementing which type of gate here? NOT gate. Okay, it can implement NOT gate. Okay, similarly if I take for this gate itself, if I give this as 0, for this one if I give a, then what is the output I am getting here? 0 plus a bar. Okay, nothing but a bar I am getting here, a bar. Okay, NOT gate. And for this one, by using this gate only, D gate. Okay, if I give some b here, what's the output I am getting here? This is this plus this, a bar plus b bar. And De Morgan's law, what is a bar plus b bar? This a bar plus b bar, De Morgan's law, nothing but a b bar, nothing but which gate we can implement up to here, from here to here we can implement NAND gate. NAND gate. And at the output if I put a inverter again, it can give this section. If I place here, okay, at the output if I place something like this, this is a bubble, if I give a 0, okay, and then I am getting a b bar whole bar, nothing but a b, I am getting a b. Okay, this entire section we are able to implement AND gate. AND gate. Okay, up to here we can implement the AND gate. Similarly, okay, suppose if I take another case here, I am taking one input a equal to 0. Okay, if I give b, then what's the output here? 0 plus b bar. Okay, nothing but b bar, NOT gate, it I am implemented. And again if I connect this one to some a here, this b bar bar, okay, what I am getting here? A plus b. Okay, a plus b, and up to here it is implementing which gate? A plus b, OR gate. OR gate. And right now for this one again, if I give a inverter something like this, if I connect to another gate like this, okay, 0, this is 0, this a plus b, if I give, I am getting a plus b whole bar, a plus b whole bar. Okay, it is giving NOR gate, NOR implementation up to here, like that. Okay, by using this gate we can implement, okay, by using this one we can implement a NOT gate, we can implement AND gate. Okay, we can implement NAND gate, we can implement OR gate, we can implement NOR gate. Okay, here see the options here, like that. See the options. NAND gate can be implemented, NOR gate can be implemented, AND gate can be implemented, OR gate can be implemented. But here option cannot, they given cannot, you can implement. Okay, and multiple select question. Okay, too many options can be correct here. Here answer is B and C are correct. Both B and C are correct. Both B and C are correct. Clear everyone? By using some, they invented some gate which is here. What is the output of this gate? A plus B bar. Okay, A plus B bar. By using this gate I can implement NOT gate, I can implement here NAND gate, I can implement here AND gate. and I can implement OR gate, we can implement NOR gate, like that we can implement by using that gate itself. Okay, right, very good. This is a question given from digital electronics. Okay, and see the question for the state transition diagram with states A, B, C, state A, state B, state C. Probabilities P1, P2, so on, P7 is as shown in figure. State probability transitions. Okay, which of the following statements is or correct? Okay, this is also MSQ question, multiple select question, MSQ, multiple select questions here, MSQ. Okay, sir, they given the probabilities. Let us check this one. Okay, see here, everyone, notice here, this state diagram itself I taken again. Let us see what are the probability of going from state A to state B, state C. Here I can move to state A to state A itself, or state A to state B, or state A to state C. Okay, what is the probability from state A to state A itself? P7. Okay, probability from state A to state B, P1. What is the probability from state A to state C? P4 is given. Okay, and from here itself, sum of probabilities we know. Okay, the sum of all the probabilities always equal to 1. This P1 plus P4 plus P7. The sum of all the probabilities should be equal to 1. Similarly, what is the probability from state B? State B to state B, we can move the probabilities P2. State B to state A, we can move here with probability P3. That's all. Nothing. We can't move from B to C here. What is the probability here? P2 plus P3. Okay, equal to 1. Right, sum of probabilities always equal to 1. Similarly, state C, from state C I can move to state C itself, state C to state A here. What is the probability state C to state C? P5. What is the probability from state C to state A? P6. And sum of probabilities P5 plus P6 equal to 1. Okay, that's all is information. And here P1, P4, P7, option B is correct. And P1, P2 plus P3 is 1, P5 plus P6 also 1, P2 plus P3 is 1, P5 plus P6 also 1, and both are equal here. And first option, if you notice here, P2, P4, P7, P2, this is P2. If I talk about the first option, this probability P2, this another probability P4, some P7, where is P7? This is P7. And they are not at all related to each other. P2, P7, P8, okay. See state A, P7, okay, so C, P4, but A to B, I can talk like P1, but they are given some other, okay, this is an unrelated thing, that's why this is not right. And P1, P3, P1, P3, and P4, P6, okay, these are also not related, that's why option C also wrong. That's why correct option for this given question. This is also MSQ question. Option B and option C. Option B and option D both are correct. Option B and option D both are correct here. Clear? Let us move on to next one. Okay, here Fourier transform. Okay, you can guess the subject. Okay, this came from signals and system. Okay, the Fourier transform x of j omega of the continuous time signal x of t equal to, they are asking for this signal, what is the Fourier transform? What is Fourier transform of this signal they are asking? Okay, directly there is no answer. Actually, we learned something, e power minus at signal into u of t. For this signal, what is the Fourier transform? 1 by a plus j omega, right? Similarly, suppose e power at u of minus t signal is given. What is the answer for this one? 1 by a minus j omega. 1 by a minus j omega. If I add these two, we'll get e power minus a mod t. Okay, u of, okay, e power minus a mod t. For this one, what is the answer? Add these two. We'll get 2a by a square plus omega square. Seems to be, okay, omega square. Maybe here t square, 1 plus some t square, this is something like omega square, right? Or right now let us put a equal to 1 here. If I put a equal to 1, this is e power minus mod t. Okay, this value is nothing but 2 by 2 square plus omega square. Sorry, 2 square, Okay, this is 1 square plus omega square. 2 into 1 divided by 1 square plus omega square. Okay, I am using this relation. Okay, what is the Fourier transform of e power minus mod t? E power minus mod t, what is the Fourier transform? We got here 2 into 1 by 1 plus omega square. 2 into 1 by 1 plus omega square. Right now, let us do one thing here. Let us multiply by t on both sides here. T, not t. Let us use this property t. T into e power minus mod t. If I use this property t into e power minus mod t, and we know one property. This is f of t. If f of t, Fourier transform is f of omega or j omega. Okay, then if I multiply t, okay, t into f of t, this is nothing but j into d by d omega of f of omega. This is a property we know, Fourier transforms. You have studied in signals and systems, or you have studied maths also. Right, here same way, this is j into d by d omega of f of omega, nothing but 2 by 1 plus omega square. 2 by, okay, j into d by d omega of 2 by 1 plus omega square. Okay, j, differentiate this one, u by v rule. If I u by v rule, okay, 1 plus omega square into differentiation of numerator 0 minus numerator into differentiation of denominator. Differentiation of denominator constant 1, 0, 2 omega square will become 2 omega divided by denominator whole square. Like that. This is the differentiation. Okay, this is 0. This is 2 into 2 omega minus 4 omega by 1 plus omega square whole square. Okay, this is t into e power minus mod t. Okay, t into e power minus mod t. This is a Fourier transform. Or right now itself here, tell me. This, I am taking this one, that side. Okay, there is a j also. J term is also there. This is j. Okay, right now, okay, here, if I take j and 4 that side, minus t by j4, or minus, okay, minus j, this minus j when goes to that side becomes a plus j, right? Minus j when it goes to that side becomes a plus j into t into e power minus mod t. This Fourier transform nothing but, okay, or 4 also I will take this side, 4 divided by 4. Okay, this is nothing but omega by 1 plus omega square whole square. 1 by omega square plus whole square. That's all. Okay, right now again it seems like, how it seems like here, this is entire thing f of t. Notice here, suppose this is f of omega. Okay, let us see here what they asked us to calculate. What is the Fourier transform of t by 1 plus t square whole square? Some function like this. We know one property called duality property. What is duality property? Small function of t, we got some capital function of omega. Then this capital function of t, if I want to find, is nothing but 2 pi into f of minus omega. That's all. 2 pi into f of minus omega. Finished. Therefore, this t by 1 plus t square whole square. What is the Fourier transform? 2 pi into, okay, here 2 pi into this function, you substitute wherever t is there, you substitute by minus omega. Okay, j by 4, and t is there, you substitute minus omega into e power minus mod of minus omega. Okay, this is pi by 2. Okay, j is there, and minus, okay, minus omega e power minus mod omega. And finished. You choose the correct answer here. Right? Very good. You choose the correct answer from these options. They asked the j kept the j denominator itself, okay, j denominator itself here, or if I take minus j in the denominator, answer you will get plus j, okay, 2j, this is omega e power minus mod omega, okay, you choose the correct answer option. Pi by 2j omega, pi by, you got answer pi by 2j into omega e power minus of omega. Which is the correct answer here? Pi by 2j, D option is the correct answer. That's all. Play with your Fourier transform properties here. That's all. If you do directly by taking that integral x of t e power minus j omega t, it takes time. Okay. Do in a smart way, everyone. Finished. Like, let us move on to the next question. Let x1 of t equal to e power minus t u of t. x2 of t is given as u of t minus u of t minus 2. Where u of t denotes the unit step function. What is y of t? Okay. Convolution of x1 of t and x2 of t. They are asking that value at t tending towards infinity, that y of t, okay, convolution of this thing, y of t nothing but x1 of t convolution with x2 of t, right? They are asking this convolution value at infinity, t tending towards infinity. Okay, let us do this question here. Sir, let us do by using Laplace, okay, Laplace. Let us use Laplace here. Suppose x of t is given, then what is x of s, x1 of s here? This Laplace of this one, e power minus t nothing but 1 by s plus 1. That's all. Okay, for x2 of t, u of t minus u of t minus this Laplace transform nothing but this, for u of t 1 by s, delayed by 2 units nothing but e power minus 2s, okay, 1 by s. Okay, we got so here, let us apply Laplace for this one, this y of s. This y of s equal to x1 of s, convolution time domain nothing but multiplication frequency domain, x1 of s into x2 of s. Laplace transforms, okay, convolution one domain nothing but multiplication other domain, just make use of this one. Therefore, this is 1 by s plus 1 into that value, okay, if I take this is 1 e power minus 2s divided by s. This is a y of s. Finally, y of s you got like 1 by s into s plus 1 into 1 minus e power minus 2s. Finished. This is the y of s. But what they are asking us here, what they are asking us to determine, they are asking us to determine y of t as t tending towards infinity. But we know the information only about y of s right now. And we know one small property or theorem called final value theorem. What is final value theorem? Final value theorem. This final value theorem, what it states? Okay, I can calculate this y of t or y of infinity as limit t tending towards infinity. Okay, it will give the final value. How to find this value? Limit s tending towards 0, s into f of s or y of s here. Okay, y of s. That's all. And this theorem, when you can apply this theorem, only provided all the poles are lying on the left half of the S-plane or stable systems only you can apply. And here for this one, if you plot the poles, this is poles here. Okay, system is a stable system, okay. And for this one, we can comfortably apply this final value theorem. Therefore, this is a limit s tending towards 0. This is s into, what is y of s here? 1 by s into s plus 1 into 1 minus e power minus 2s. Okay, here anything getting cancelled here, anything getting cancelled here, this is getting cancelled, and the limit s tends to 0. Okay, this is y of infinity value we are trying to calculate, y of 1 minus e power minus 2s by s plus 1. Okay, and I am not getting any 0 by 0. Okay, I am not getting any 0 by 0. That's why I will substitute the value of s equals 0 here. When s equals 0, e power 0, 1, e power 0 divided by 0 plus 1. This is 1 minus 1 by 1. What is value? 0. Answer for the given question nothing but 0 is the right answer. 0. It's a NAT question. Fill in the blanks, you have to Right, the answer 0 is the right answer for this question. 0. Done everyone? Following everyone? Okay, very good. Up to now, very, very easy questions. Let us move on to next question. Okay, the outputs of 4 systems they given: S1, S2, S3, S4. S1, this is the system S1, S2, S3, S4. System S1, when sign t is given, it is inverting the okay, sign of minus t. It is giving the output sign of minus t. Sign t is given to system 2, it is giving advanced signal, sign of t plus 1. When sign t is given to the third system, it is giving sign of 2t. When sign t is given to the fourth system, it is giving square of that signal, sin square t. Then what they are asking here, which of the following, okay, to the input sin t for all the systems shown based on the given system is or are definitely not LTA. Here is or are definitely not LTA. Okay, means which are not LTA they are telling. Okay, first of all tell me linear time invariant system. Do first. Which systems are linear, which systems are non-linear. If you notice here, this system, okay, it will say linear. But if I delay the input t minus tau, output is delayed by different way. It's a non-time varying system. It's a linear system but time varying system. This system sin of t plus 1, okay, sin t plus 1 is a linear system. Time also invariant system itself. Time invariant systems. Okay, here this system sin t, okay, sin of 2t, sin of 2t, this also linear system. Linearity, what is the linearity property? Which obeys both homogeneity as well as additivity or superposition principle. Okay, like you will check by giving the inputs a x1 of t plus b x2 of t. Similarly, we will check the outputs a into y1 of t plus b into y2 of t. You are getting same way, then it's a linear. All are linear systems. So all are linear system. This system is a non-linear. Okay, and if I delay the system by tau, this okay, only input if I delay 2t minus tau, sin of if I delay only 2t minus tau. If I delay output, this entire output if I delay sin of 2 into t minus tau. Okay, this is sin of 2t minus 2 tau you are getting. Whether both are same? No, that's why it's a time varying system. Time varying system. Next, this sin t sin square, okay, it will not obey that homogeneity as well as additivity principle. This is a non-linear system, but it's a time invariant system. Okay, as a whole, tell me as a whole, this is the LTA system. This is only LTA system. Okay, this is not LTA. Okay, linear but time varying, linear but time varying, non-linear but time invariant. Okay, and in the question they ask not LTA. In the question, if you notice here, which systems are not LTA? The only LTA system, this is the S2. Okay, not LTA here means S1, S3, S4, A, C, D, all are correct. It is also MSQ question, okay, multiple choice question. Okay, 3 options are correct here. Which is not a LTA? They ask which is not an LTA system. Let us, okay, move on to next question. Okay, answer here, that's the thing, right? Okay, the trans function of a system is given like this. Okay, trans function. The system is purely delay. Okay, so that's all. That's the trans function, magnitude function they given like this. The system is purely delayed system for the input applied between frequency range minus alpha to alpha, and the relation between input and output spectral density. Okay, they are asking us to select one of the answer. Okay, and we know one thing. Suppose some system is there. Okay, x of t is the input. If I apply to a system, x of t is the input. If I apply to the system, okay, I am getting the output y of t. Okay, then when the system is said to be delayed system, this y of t equal to x of t minus some delay td or t naught, whatever it may be. Okay, y of t equal to x of t minus some delay td. Okay, if you talk in terms of system function h of t or h of omega or h of f, okay, the output by input, if you apply here this h of f, what will get? Magnitude is 1, you will get e power minus j omega td you will get here. And if you plot this magnitude response and phase response for this one as a function of omega or f, okay, or f. Omega or f. Omega means 2 pi f only. Okay. If I plot this magnitude function, magnitude of h of f or h of omega. If I plot this magnitude here, this seems like an all pass filter, constant everywhere, one only, irrespective of the frequency, we will get the response like all pass filter. And if I plot the phase response, angle of h of f. Okay, this is the angle minus j. Okay, this is this can be written as 1 at an angle minus omega td. Okay, and angle, if I plot this angle, how this angle will be something like this, passes through origin. Okay, passes through origin with slope minus omega td. Okay, minus td is the slope here. This is all pass filter characteristics for a delayed system. From this information we have to solve. So here the system is purely delayed system for the input applied, okay, between the very important point. In this one key point is in the frequency range only they are asking minus alpha to alpha, okay, from frequency range from minus alpha to alpha. Actually the system is all pass filter from minus into plus infinity. Only in this range they are asking minus alpha to alpha. Definitely characteristics is like this only, minus alpha to alpha characteristics. Usually all pass filter from minus into plus infinity, only they are seeing between the limits minus alpha to alpha. Okay, this option is correct answer. Between this one, actually from minus into infinity is like this, but only between this range like this constant. Okay, the relation between input and output power spectral densities. Here what is the relation between power spectral densities? Actually power spectral densities, okay, power spectral densities. If I talk about power spectral density, notice here Sy of f is nothing but modulus of h of f square into Sx of f. This is the relation between input power spectral density and output power spectral density. And here this magnitude of h of f is always 1. Okay, therefore this 1 square nothing but Sy of f, or your Sy of f equal to Sx of f itself here. Okay, for this delayed system, therefore the relation between input output, right, both the statements are correct here. S1 is correct, S2 also correct. Option D is the correct answer for this question. Clear everyone? Okay, this is also question from signals and systems. Simple thing, they asked, they given like it's a delayed system. For this delayed system, option A, between the range only they asked. If not, they not mention the range. If they have not mentioned the range, that's wrong. Okay, since they mentioned the range between minus alpha to alpha, then it's the right answer. Both the statements are correct. Okay, controls, some question, yeah, by seeing the diagram you can think like it's a root locus. The locus diagram, root locus of a closed loop system with unity feedback, okay, and the transfer function k into g of s in the forward path is shown in figure. K is valid from 0 to infinity, select the transfer function g of s. They are asking, okay, here different paths. If I notice here, this is one path going like this, another path like this, another path like this, another path like this, another path like this. How many paths here? 1, 2, 3, 4, 5. 5 paths. Okay, that 5 paths directly giving the information like all are away. All are away means poles only, break away. All are away only. No in. Okay, right. Then this option cannot be right. Okay, no zeros. All are away from that. And at this point, if you notice here, this is the origin. Okay, this is at a distance of 1. Okay, at a distance of 1 means this is LHS side 1. Okay, from this one, how many here breakaway? 1, 2, 3, 4, 5. 5 poles. Either answer can be A option or B option. That's all. 5. This is not 6. Okay, A or B. Okay, and we know one thing directly. What is the angle here? 2k asymptote angle, 2k plus 1 into 180 divided by p minus z. Okay, this is a 2q into 180 divided by p minus z. What is p? 5, no zeros here, this is the value. Or this is a 2q plus 1 divided into 360 degrees, 36 degrees. Okay, 36 degrees. If I put the different values of q, 0, 1, 2, 3, 4, okay, 5 values, okay. And if I put q equal to 0, what's the angle here? 1 into 36, 36 degrees. 2 q, okay, this is 1 into 36, 2, 3 into 36, 5 into 36, 7 into 36, 9 into 36, okay. What the value here? This is 36 degrees, this is 108 degrees, this is 180 degrees, this is 252 degrees, this is 324 degrees. Okay, these are the asymptote angles. There's 36 degrees here. Okay, this is 108 degrees, 108 degrees, and this is 180 degrees. Okay, and this is 252 degrees. Okay, this is minus 36, or from here this is the 324 degrees. Okay, answer is option A is the right answer. B is the right answer. A simple question here. By seeing that one directly we can say that 1 by s plus, okay, right, control systems. Okay, another question they have given an even polynomial p of s, okay, given as a s power 4 by 5s square, sorry, s power 4 plus 5s square plus 4 plus k, where k is an unknown real parameter, the complete range of k for which p of s has its roots on imaginary axis. Here this is actually polynomial s power 4, no s cube term, okay, 5s square, no s term, okay, plus some constant 4 plus k. All the odd terms are missing, only even, okay, that's why they given an even polynomial. This type of questions can be solved by using Routh-Hurwitz criteria easily, RH criteria, okay, RH criteria. Here I am writing s power 4, s cube, s square, s power 1, s power 0. Okay, write the quotients here. This quotient here 1, this quotient 5, this is 4 plus k. Okay, and this everything becoming 0, 0, 0. Yes or no? No quotients there. At that time, what we'll do? Okay, at that time, what we'll do? We'll take this one, s power 4 plus 5s square plus 4 plus k, differentiate it, we'll get the 4s cube, 10s and 0, okay, and right now s cube and 10 quotients are nothing but 4, 10, and here I can cancel 2, this becomes 5, okay, right now this is 2, 5. And right now, okay, let us write here, everyone, let us write this one. This quotient here, 2 into 5, 10 minus, okay, 10 minus 5 divided by this one, 2. This is 5 by 2, 2.5, okay, and this value nothing but 2 into this value minus 0 by this value, we will get 4 plus k. Okay, this value 5 by 2, 2.5. Okay, let us write this one, everyone. Let us write this one. Okay, this minus this, okay, this minus this by this value. 2.5 minus 2.5 into 5 minus this 2 into 4 plus k divided by 2.5. Okay, no other quotient there. That's all. This one. This is okay. We'll come back again. Again here, this into this, and nothing quotient here. No quotient here. 0. Okay. This minus this by this value. If you would do it here, you will get 4 plus k. And the first row. Okay. First row. These are the first row. This is 1. This is 2. this is 2.5, okay. This is a 12.5, 12.5 minus 8 plus 4k, 12.5 minus 8 minus 2k divided by 2.5, and this is 4 plus k. First row, this is a first column, okay. First column we got like this, okay. Here itself we can answer directly. First column, when you will have imaginary roots, okay, when this entire row becoming 0, then you have imaginary roots. Okay, here this value should be greater than 0, greater than or equal to 0, equal to 0, greater than equal to 0. This value also should be greater than equal to 0, okay. Okay, say imaginary roots only, no RHS roots, okay. It should not have any sign changes, okay. This positive, 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 this should be positive, this should also be positive. 12.5 minus 8, 4.5, 4.5 minus 2k by 2.5. This value should be greater than or equal to 0, or 4.5 minus 2k, this value also should be greater than equal to 0, okay, or 4.5 value should be greater than equal to 2k, or 2k should be less than 4.5, or k should be less than 4.5 by 2 or 9 by 4, okay, less than or equal to 9 by 4. Similarly, this one, you take this one, this 4k, 4 plus k should be greater than or equal to 0, or k should be greater than or equal to minus 4. And combine these two, okay, we got to k should be greater than or equal to minus 4, and k should be less than or equal to minus 9 by plus 9 by 4. And if you combine these things, minus 4 less than or equal to k less than or equal to 9 by 4 is the right answer. Which is the correct option here? This C is the correct answer for this question. C is the correct option, is dash. Finished, that's all. Control systems, very easy question. Okay. Another question, if you move on to next question, what they are given, find the steady state error ESS due to the unit step disturbance D. Find the steady state error ESS. Steady state error. Error, how it is defined? This is a reference input here. You are applying a reference input R of t. Okay, you are getting a control of output here, Y of t or C of t. Okay. And the difference between this output and input nothing but your error signal E of t. This is the E of t. Okay, the difference between that input and output nothing but your error signal E of t. Okay, right now here this R of t equal to 0. Some disturbance is getting added up, unit step disturbance is getting added up. Then what is the steady state error they are asking here to find out? Okay, everyone, let us derive something here. Okay, everyone, notice here. I am talking everything in terms of a frequency domain, a Laplace domain. Okay, Laplace. If I convert into Laplace, this is R of S. Okay, R of S. This is E of S. Let us assume this 10 as G1 of S. Let us assume this as G2 of S. Okay, this is, let us assume this is a D of S. And this output be Y of S. Output be Y of S, everyone. Okay. Right now, tell me, this is E of S. Okay, this is E of S. E of S into G of S. Here I am getting multiplication, E of S into G of S. And this D of S getting added up. Okay, here this one nothing but D of S plus E of S into G of S. D of S plus E of S into G of S. Okay. Next, this function multiplied by this one will give the output Y of S. What is this Y of S? G2 of S into D of S plus E of S into G of S. That's a Y of S. Clear, everyone? Okay, right. And right now tell me, what is this this error E of S. This error E of S, okay, nothing but this r of s minus y of s, r of s minus y of s, that error here, r of s minus y of s, and reference input 0, okay, this Laplace transform 0, this y of s only, e of s, okay. Therefore, this e of s equal to minus y of s, minus y of s. What is y of s? This is the y of s, okay. This is minus g2 of s into d of s plus, okay, this is g1, this is g1, this is g1, okay, e of s into g1 of s, okay. I am writing this one again, this error signal here, this error e of s equal to minus g2 of s into d of s plus, okay, d of s plus e of s into g1 of s, e of s, e of s into g1 of s. We need to find the error, steady state error, okay. This is e of s, here also you have e of s, separate the terms containing e of s here, okay. This is e of s equal to minus g2 of s into e of s minus g2 of s, g1 of s into e of s, okay. This term I am taking this RHS, LHS, e of s into 1 plus g1 of s, g2 of s, okay, is equal to minus g2 of s into d of s. Okay, then what is steady state error e of s? This steady state error nothing but g2 of s into d of s divided by 1 plus g1 of s, g2 of s. That's all. g1 of s, g2 of s. But what they are asking us to determine steady state error as t tending towards infinity, they are asking, okay. And let us use this final value theorem again, final value theorem, final value theorem, okay. Then this final value theorem, this e of t as t tending towards infinity, limit t tending towards infinity, this value nothing but limit s tending towards 0, s into e of s, okay, s into e of s. This is the limit s tending towards 0, s into, what is e of s given here? We got here minus g2, okay, of s, d of s divided by 1 plus g1 of s, g2 of s. That's all, okay. And tell me what is the d of s here? Unit step, okay. D of s here, d of s equal to unit step u of t, okay. U of t, what is Laplace transform of u of t? 1 by s. This is nothing but 1 by s, okay, 1 by s. Next, therefore, this is the limit t tending, s tending towards 0, s into minus g2 of s, okay. After some time we will substitute g2 of s into 1 by s here divided by 1 plus g1 of s, g2 of s. This s getting cancelled. Therefore, limit s tending towards 0 minus g2 of s by 1 plus g1 of s into g2 of s, okay. This is your steady state error at infinity, e of infinity. That's all. Substitute, let us substitute these things here. This is g1, this is g2, okay. Let us say g1. Here you got e of infinity like a minus, okay, limit s tends to g2 by 1 plus g1 g2, limit, okay, limit s tends to 0 minus g2 of s divided by 1 plus g1 of s into g2 of s, and g1 of s given as 10, g2 of s given as 1 by s into s plus 1. Let's check it out. G1 given as 10, 1 by s into s plus 10, okay, 1 by s into s plus 10, okay. Substitute this value. So then what is steady state error? okay, limit s tending towards 0 minus g2 1 by s into s plus 10 divided by, okay, 1 by 10 into 1 by s into s plus 10. Just substitute the value, that's all. Substitute s equal to 0. It's minus into numerator okay, e of s equal to, okay, substitute these values here. Substitute these values, find it, complete the things. Okay, right, here if I multiply here, outside is right 1 by denominator also, okay, notice here 1 by s into s plus 10 okay everyone, okay, let us do it here. 1 by s into s plus 10 divided by, okay, s into s plus 10 plus 10 divided by s into s plus 10. LCM I am taking denominator, these two getting cancelled. Limit s tends towards 0. Limit s tends towards 0. Okay, therefore e of infinity. This e of infinity nothing but limit s tends towards 0 minus sign. Just I am substituting those values here. 1 by, okay, 0 into 0 plus 10 plus 10. Okay, that's all. This is minus of 1 by center 0 plus 10, or this value nothing but minus 1 by 10, or this is minus 0.1. This is the steady state error, e of infinity. This is a question for this answer. Okay, e of infinity, steady state error nothing but minus 0.1 is the right answer. That's all. Control systems, easy question here. No need to remember any formulas. Okay, if you play with the basics here, that's all. Okay, steady state error they asked us to calculate. See the next question. Let us move on to next question. Switch on to the next question. The Nyquist plot of the system g of s they given, okay, g of s. For k equal to 1, they given this Nyquist plot, okay, for k equal to 1 as shown in figure. Okay, for k equal to 2, the number of right side closed loop poles, okay, if it is known that g of s has no poles on the right half of the s plane. So here, suppose if you take the contour, suppose contour, if they taken the contour like this, contour, no open loop poles, okay, no poles means no open loop poles. Number of encirclements is nothing but p minus z, where p is the number of open loop poles, z is nothing but the number of closed loop poles. Okay, when z equal to 0, system is stable system. Okay, we used to do like that. Right now what they asking us is, what the information they given, no poles, open loop poles, they given the information p equal to 0, and they are not given the z, they are asking us to determine z, closed loop poles, and the number of encirclements we need to find based on this information. Number of encirclements we need to find based on this information. But here they given the information about this Nyquist plot for k equal to 1. For k equal to 2, the number of right side closed loop poles information they are asking. Okay, let us do this question. See here, for k equal to 1, they have given, for k equal to 2, this becomes into 2, this magnitude becomes 0.8. This from here to here, for k equal to 1, this is 2.8, and this becomes 1.6, 1.6, right? And right now we'll see the encirclements. See here, and this length is 1.6, this is 1.8, sorry, 0.8. Okay, this is 1.6, this is 0.8, okay, and this point, okay, -1 plus j zeros will be somewhere between 1.6 and 0.8, -1 plus j 0, this is our reference point for encirclements. From here what I am doing is I am drawing a line. It is inserting this Nyquist plot at 2 points, here, here, and the number of encirclements I need to calculate here. This is clockwise, this also clockwise. If the encirclements is in the anti-clockwise, positive. If the encirclements in the negative side, in the clockwise, then it is negative, right? Number of encirclements n for this one nothing but -2, since clockwise encirclements twice, okay, and since n equal to p minus z and no open loop holes minus z, and here encirclements nothing but -2. Therefore, z minus z equal to -2, z equal to 2. Answer right now closed loop poles. Closed loop poles. Okay. Information. How many closed loop poles? Nothing but here z equal to 2. Z equal to 2. Okay. If they still ask, system is unstable system. That's all. Finish. Simple question. Nothing. No complexity. Simple. Okay, just a basic encirclements question, that's all. Let's move on to next question here. Consider two systems. This also question came from your control systems itself, right? G1 of s given 10 by s square plus s plus 1, G2 of s given by 10 by s square plus root 10s plus 10. They are asking percentage peak overshoot, steady state output, damped frequency, steady state error. Okay. Here let us take these two systems. Okay, G1, what is G1 of s? This is 10 by s square plus s plus 1. Okay, or if I keep 10 outside, this is 1 by s square plus s plus 1. G2 of s, okay, they given G2 of s. What is this G2 of s? 10 by s square plus square root of 10 into s plus 10. Okay, if you compare with the our characteristic equation, this bottom part, if I, okay, it seems like a second order only. Okay, second order response, something like s square plus 2 zeta omega n into s plus omega n square, right? Here also same, 10 into something like omega n square by s square plus 2 zeta omega n s plus omega n square, but it is omega n1. Okay, first system, let us 1 zeta 1 omega n1 omega 1. Second system, let us assume omega 2 omega n2 zeta 2 omega n2. Now let us compare and tell me what is the value of omega n2 here. Omega n2 here nothing but root 10. 2 zeta omega n equal to root 10. If I compare here this then what is the value of 2 zeta here? This is root 10 cancel 1, or zeta 2 equal to 1 by 2 we got here this information. And here if I compare here, omega n1, this omega n1 equal to 1, okay, 2 zeta omega 1 equal to 1, okay, then 2 zeta omega 1 equal to 1, zeta 1, for this one nothing but you got like 1 by 2. And here these two systems, if I compare, which parameters are same? Okay, this omega n different. Okay, and see this option, damped frequencies. Damped frequencies omega 2. If I calculate as at omega, how to calculate omega d damped frequency? Omega n into square root of 1 minus zeta square. Omega n's are different. For this one omega n 1, that for that one omega n root 10 different. Therefore, damping frequency same is wrong answer. Steady state errors, okay, also not same. Steady state error different here. Steady state output also, if I convert into time domain, write in a proper order, you will get some e power minus t by 10 times of output will be this. I write s plus 1 by 2 whole square plus some constant. If I convert into time inverse Laplace, something like e power time something sine 10 into. Okay, if I convert this one, okay, I will get some. Okay, if I take this, you will get something like 1 into e power minus root to 10 by 2 into sine of some factor. Okay, steady state values. Okay, different values, steady state values also not same, errors also not same, and zeta here, zetas are same. For zeta here, both are same. If zetas are same, we can calculate peak overshoot. How to calculate peak overshoot? Tell me. Peak overshoot, everyone. If I calculate peak overshoot, percentage peak overshoot, how to calculate peak overshoot? E power minus zeta pi by square root of 1 minus zeta square into 100. Okay, peak overshoot. If I go to peak overshoot, this percentage peak overshoot, MP. How to calculate this one? E power minus zeta pi by square root of 1 minus zeta square into 100. Only zetas are same for both the systems. Peak overshoot also same for both the system. That's why. What is the correct answer? Tell me. This is the correct answer. Percentage peak overshoot for both the systems is same. That's all, right? Very good. Let's move on to next question here. Okay. Consider the circuit shown with an ideal op amp. The output voltage V0 is dash, round off to 2 decimals, everyone. Okay. Consider circuit shown with an ideal op amp. The output voltage V0 is dash, round off to 2 decimal places. Okay. This question came from analog. Okay. We can use the principles of networks also here. Right. This is the diagram. And here this is grounded to R. This is 2R connected to 1.6 volts. R. This is 2R connected to ground. R. 2R connected to 1.6. R. 2R grounded. 2R. This is grounded. Okay. This is 3R. Plus 15 minus 15, this is V0 they are asking her. And tell me how many inputs are applied here? 2 inputs, 1.6 volts here, 1.6 volts here, 2 inputs applied here. Okay, whenever different inputs, many inputs are there, we can use superposition theorem to calculate the response, SPT, superposition theorem. Assume only this source acting alone, okay, find the output. Assume only this source acting alone, find the output. Okay, and another thing here, this positive terminal, non-inverting terminal connected to ground, and the inputs are applied to the inverting terminal. Okay, inverting terminal. And here, if I know this information, see, inverting terminal, non-inverting terminal connected to ground, and if this resistor is RF, okay, if this is resistor is suppose R1, suppose, okay, and input applied here, then what is the output? Input applied to inverting terminal. Okay, this positive terminal or non-inverting terminal is grounded. Then what is the response output for this one? If you are assuming this is Vi, this output V0 equal to minus RF by R1 into Vi. That's all. For for inverting kind of thing, gain minus RF by R1. If you know this one, we can solve this question here easily. Okay, 2 inputs are applied here, 1.6, 1.6. Let us take. I am assuming only this source acting alone. Okay, this shows neglect. How to neglect this ideal voltage source? Replace by short. Assume only this source acting alone. Let us find this output voltage V01, or let us try to find here. Let us try to find this voltage here, Vx. Some voltage here. Let us try to find this V1. Okay, everyone, simple. Follow me. Follow me, everyone. Everyone, just follow me. Right now, if you talk about resistance, okay, resistance, only Thevenin resistance, suppose, or let us try to simplify this network here. Let us try to simplify this network. Everyone, notice here, I am talking about this part of circuit here, this part of the circuit. If I talk about this part of circuit, it seems like 2R, we are giving 1.6, this is a 2R. or I can write like this 2R, this is 2R, this is grounded, this resistor I am talking here, this resistor I written here, 2R grounded. For this 2R we are applying a 1.6 volts. Noticed? Got the point? Let us find this value. Let us try to find this value Vx1. Here let us find this voltage Vx1. Thevenin equivalent I am trying to find, that's all. This voltage division rule, both are connected in series. This voltage division rule equally divided 2R by 2R plus 2R into 1.6. Okay, this are 1.6 divided by 2. This Vx1, this voltage here nothing but 0.8 volts. 0.8 volts. This Vx1 we got 0.8. Okay, clear? This Vx1 we got 0.8 volts. 0.8 volts Vx1. Okay, this Vx1 we got 0.8 volts. Finished. Okay, this entire part of the network can be replaced by Vx1. And what is the Thevenin resistance? Deactivate this one. This 2R parallel. What is the equivalent resistance? If I want to find the Thevenin resistance here, okay, this if I look from here, what is the RTH or Rx? Nothing but 2R parallel with the 2R. 2R parallel with 2R, nothing but R itself. Okay, therefore this entire network, okay, this entire network here, this entire network can be replaced by VTH series with RTH, Vx1 series with Rx. What is the Vx here? 0.8. What is the Rx here? R. Okay, right, completed. Up to this part completed. I am erasing here. Okay, I am not talking about this one. Finished, everyone. Notice here. Okay, right now this part of the network not there. And what is the equivalent here? Equivalent here, it seems like a like this. This is 0.8 volts and this resistance is R connected here. 0.8 volts connected here. 0.8 volts connected here. Everyone please. Okay, this part of circuit is not there. Okay, this seems like a resistor. Okay, this part not there. 0.8 volts R connected to R. Okay, right now again this R and R series, this equivalent nothing but 2R. Okay, and right now this part of circuit, let us talk about this part of circuit. Okay, again this R, okay, this R here, this R here, and this is a 2R, and this is a 0.8 volts. Okay, grounded. Let us try to find the Vx2 here. Vx2. Okay, tell me what is this Vx2 again? Voltage division rule. Okay, again these two resistor series. This is 2R, this is 2R. 2R by 4R, 1 by 2 into 0.8. What is value then? 0.4 volts. And similarly, what is the RTH here? RTH looking into these terminals or Rx2. This resistance both will be parallel. 2R parallel to R. Okay, therefore here again you got this voltage as a V as 0.4 volts. This is a R. Okay, this is R. We are trying to simplify this network at different parts, different parts. Okay, right. Finally, this entire network up to here we have simplified. Up to here, what is voltage here? This seems like a like this. Voltage is 0.4 volts. This resistance is R. This entire network. Rx2 nothing but okay R. Okay. Again, let's move on to this part. Everyone, this concept used to asked in earlier in IES many times. Okay, Right, again this, let us talk about this one, this resistor and this resistance. Okay, this is R, this is R, this is 2R. Okay, grounded. This is 2R, this is R. Okay, this right now this is 0.4 volts. And again voltage division rule, you will get 0.2 volts. Okay, resistance looking into this elements nothing but R. Right now, okay, again this entire part. Right now up to here. Up to here, from here to here, if I see, okay, up to from here to here, if I calculate, if I see this network, it seems like a 0.2 volts, this resistance here, okay, this is R, this is 0.2 volts, 0.2 volts, everyone. This network is not there. And again, here R, okay, this is 2R, again voltage division rule 0.2, getting divided between this and this, and what is the voltage we are going to get here? Directly I am writing here. Okay, next, again voltage division rule, and this resistor and this R, okay, parallel the series, okay, and right now directly I am writing this point. This is R, actually up to now we have seen this is R, this is 0.2 volts, okay, and right now R series 2R, again 2R parallel, okay, voltage division rule, okay, this voltage division rule up to here directly I am writing here. Notice here everyone, from this point here, if I write here, this entire part of the network can be replaced, okay, directly this is R, okay, this is 0.1 volts, 0.1 volts. Okay, right now we got like this, R and R, this is 3R, we got this 0.1 volts, okay, this is minus, this is plus, this is 3R, okay. When this source acting alone, 1.6 acting alone, we found out that response like this, okay. Similarly, let us assume only this source acting alone. How to eliminate this source here? Shorted, okay, short. Let us find the response only due to this source. First directly neglect, okay, simplify this one, 2R, how they connected to each other? Parallel, R, this R series 2R, again this 2R parallel, R again series, okay, 2R. Up to here this network, up to here this resistance is 2R with respect to ground. Okay, let us start again, same how we did previously. Here, right now, I am interchanging here. This is 1.6 2R, I am writing here, this is 1.6 2R, and this is 2R with respect to ground here. Everyone notice here, this 2R with respect to ground, I written here. This 2R with 1.6 volts, I written here, 1.6 volts. And right now again voltage division rule, this is 0.8 volts and resistance nothing but here RTH grounded, deactivate this one, 2R parallel R. Therefore up to here if I calculate, up to here if I calculate, what we are getting here is a 0.8 volts, this is a R. Now this R to R series 2R 0.8, again this 2R, okay, if I talk here, this is again this point, this is 2R, this is 2R, this is 0.8 volts, okay, grounded. I am talking about these elements, this RR series 2R, this 2R. What is this voltage here? Voltage division rule 0.4 volts, and here this 2R parallel, okay, 0.8. Therefore, what is the effective circuit? What is the effective circuit up to here? What is the effective circuit up to here? What is the effective circuit up to here? This is a 0.4 volts. This is R. Clear, everyone? Okay, right now this circuit, this R, this 2R series, this becomes 3R, okay, this is minus, this is plus, this is 3R, okay, this is grounded, this is 0.4 volts, 0.4 volts. And if you notice here, previous diagram, this is a 0.1 3R. Okay, right now this diagram 0.4 3R 3R. Okay, and previously let us try to find V01. What is V01? This V01. If you calculate V01, tell me what is the V01 here? This V01 equal to minus RF by R1 into 0.1. What is the value we got here? Minus 0.1 volts. That's a V01. V01. Okay. For this one, V02. When this source acting alone. Okay. This is minus RF by R1 into 0.4. That's a V0. Okay. This value is nothing but minus 0.4. Then according to SPT, tell me, superposition theorem, total response V0 equal to output equal to V01 plus V02. Okay, this is minus 0.1 minus 0.4. Answer minus 0.5 volts is the right answer. Minus 0.5 volts is the right answer according to SPT, superposition theorem. Therefore, answer for this question nothing but minus 0.5 volts. What they asked here, consider the circuit shown in figure with an ideal op amp, output voltage V0. We found out when this source acting alone, output is minus 0.1. When this source acting alone, output is minus 0.4. When both are acting simultaneously, total response nothing but minus 0.5. And answer, they asked us to round off to 2 decimals. Answer minus 0.50. Okay, minus 0.50 is the right answer. Let us move on to next question here. This also question came from analog circuits. What is the information given? A circuit and the characteristics of diode D in it are shown. The ratio of minima to maximum small signal voltage gain dV out by D in is dash, rounded off to 2 decimals they asked. Okay, and if you notice this diode characteristics, they given like this. A circuit and the characteristics of diode. Okay, from this one, see here this diode, this is VD, this is ID. Just I required this information. Tell me what is this slope here? Slope 0. Okay, slope here. This is vertical axis ID, this horizontal axis VD. Okay, slope. If I calculate the slope, okay, it will give the 1 by resistance RD by, okay, 1 by resistance of the diode RD. Output is here vertical axis is current, horizontal axis is voltage. Okay, ratio of current by voltage will give the reciprocal of resistance here, current by voltage, and this is 0. That implies here resistance is infinity. In this region, resistance is infinity. When resistance is infinity of a diode, that a diode acts as an open circuit. Open circuit. Open circuit. Okay. And here in this region, notice here in this region is going on, right? Here resistance or slope, if I calculate slope here, infinity slope. Infinity. Okay, in this one. And here the slope nothing but 1 by resistance RD. 1 by resistance. Okay. And 1 by resistance nothing but here diode resistance. What is the resistance of the diode in this region? 1 by slope nothing but 0. In this region diode acting as a 0. Let us take this circuit here. 1 second. This diagram itself. Okay. Let us talk about this one. 2K, this is 2K diode, this is 2K, this is Vin. Let me draw this diagram once. This is V out. Okay, this is 2K. Here from here to here, P in, from here to here, this is V out. Okay, this is diode. And we have seen the slope of the diode, one direction of current flow, this is 0, another direction of current flow. From the characteristics they given infinity. Okay. When this is open, please tell me what is the thing. This 2K, this 2K, open. Okay, this diode is open circuit. This is a V out. This is a Vn. This is 2K, this is 2K, this also 2K. This output here, from here to V out, nothing but from here to here. Okay, from here to here. This seems like, notice here, this is 2K, this 2K, 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 2K. This is V in, from here to here, this is V in. This is 2K, this is 2K, this is 2K. V out from here to here, nothing but here to here. This is the V out. Right now, can you please tell me what is this V out by D, V out by V in? Right now, this V out by V in, nothing but voltage division rule 4K by 6K total resistance, or 4 by 6. Okay, 4 by 6. Okay, now same diagram, notice here. When this diode is short circuited, here from the diagram only I am concluded those things. This is 2K, this is 2K. They given the characteristics of diode like that. Okay, and right now this is shorted, right? And how this resistance and short parallel, anything parallel to short circuit, nothing but short only. Okay, right now this is V in. Okay, this is V out from here to here. Or it seems like this resistor does not have any significance right now. Okay, this is a 2K, this is 2K. 2K here, this is 2K. Okay, this is V in. Okay, and this is the V out. V out. And right now only two resistors, equal resistors connected in series, voltage division rule. What is voltage division rule? Tell me. V out equal to, V out equal to, or V out by V in. Okay, voltage division rule 1 by 2. This is 2 by 3 you got here, 2 by 3. Okay, you got 1 by 2. If you go back to the question here, okay, a circuit and characteristics of the diode are shown in figure. The ratio of minimum to maximum small signal voltage gain. V out by V in, we found out the voltage gains. In one diagram, we got a V out by V in. Okay, V out by V in, we got a 2 by 3. Another one, V out by V in, we got like a 1 by 2. Okay, the ratio of this something like 0.66, this is like 0.5. Okay, ratio of minimum 0.66, 0.5 minimum, this is the minimum. Okay, this is itself nothing but D out by dV in itself. Ratio of minimum, okay, 1 by 2 divided by 2 by 3. What is value? This is 3 by 4. Answer 0.75 is the right answer. Round off to 2 decimals. This is the answer. The ratio of minimum to maximum small signal voltage gain, dV out by dV in, they are asking us to calculate. Okay, 0.75 is the right answer. Clear everyone? Any right? Clear? Right, excellent. Right. Next question. Let us move on to next question. See here, this diagram op amp is given. This question is from analog circuits. Okay, an ideal op amp circuit with sinusoidal input. Okay, this V in is sinusoidal input is shown in figure. The 3 dB frequency is a frequency at which magnitude of the voltage gain decreases by 3 dB. Okay, from maximal. Which of the options is or correct? Okay, they are asking which are the options is or correct. First thing, it is acting as one question. They are asking whether the circuit acting as a low pass filter or high pass filter. If so, okay, then low pass filter or high pass filter. Another thing, 3 dB frequency they are asking. 3 dB frequency, low pass or high pass, and 3 dB frequency. Okay, right. Simple question. See, very easy question, nothing. Here we discussed filters, like transfer function, we'll write the transfer functions. Then we'll substitute omega 0, omega infinity, or s equal 0, s equal to infinity, or f equal 0, f equal to infinity. If the filter passes only low frequencies, not passing high frequencies, then that filter is called low pass filter. Or allowing only high frequency, not allowing low frequency, high pass filter. Allowing only low frequencies, not high frequencies, low pass filter. Allowing only band of frequencies, not allowing other frequencies, nothing but band pass filter. And allowing all frequencies except a certain range of frequency, nothing but band reject filter or band stop filter. Okay, like that we can conclude, right? We substituted, we did many things, right? How to identify the circuit as a filter or which type of filter? We'll check 2 points, 0, infinity. You can check f equals 0 or omega 0, omega s equals 0. Okay, right. Before that one, what is the impedance? Okay, omega. Okay, omega not required. Okay, what is the impedance here? Minus j by omega c plus 1k. Okay, here if you are assuming this as some ZF, okay, this has some Z1, okay, and input given to the non-inverting terminal, and here inverting terminal is grounded. Okay, it's a inverting amplifier. What is the V out for the inverting amplifier? Okay, minus that ZF by Z1 into V in. Okay, or V out by V in, nothing but gain. This gain equal to V out by V in. What is that V out by V in we got here? Minus ZF by Z1. Okay, right, ZF. What is the ZF here? 2K. This is 2002 kilo divided by Z1. Both the elements connected in series here. Impedance of a capacitor and resistor. This is 1K series with impedance of a capacitor minus J by omega C. Minus J by omega C. And C value they given 1 microfarad. Okay, 10 power minus something, 10 power minus 6. I can substitute 10 power minus 6. Okay, this is the gain. Okay, finished. Just tell me what is this gain when omega equal to 0? Omega equal to 0, what is the gain? Omega equal to infinity, what is the gain? Tell me, that's all. Omega 0, something by 0, infinity. This entire thing plus 1k, infinity. Something by infinity, 0. Okay, when I substitute here, this I got as 0. When omega equal to 0, denominator 1 by 0, infinity, this term infinity plus something, infinity, something by infinity, 0. When omega equal to infinity, okay, when omega 1 by infinity, 0, this term is 0, 2k by 1k, this gain equal to minus 2. From this, what we can infer, okay, what we can draw conclusions from here. Okay, I plotted gain, okay, with respect to frequency, and this function, what it is doing, it is not allowing low frequencies but allowing high frequencies, something like this. Not allowing low frequencies but allowing high frequencies. Then it is acting which type of filter? High pass filter. High pass filter. And the given question is a MSQ, multiple select question. Mean, okay, more than one answer is correct. Okay, right. Directly here, this one directly will give the information about the 3 dB frequency. RC, okay. Time constant RC, then frequency 3 dB. If you want 3 dB, okay, 1 by RC. That's all. Now tell me R value. What is R value? R value given as 1K, C value given as 1 micro. 1 micro. Okay, this is 1 by 1 into 10 cube into 1 into 10 power minus 6. Or this is 1 by 10 power minus 3, or this is 10 cube. Okay, so many hedges. 10 cube, so many radians per second. Okay, radians per second. Omega, okay, this is giving the information about omega 3 dB. Okay, this value omega, so many radians per second. 1000 radians per second is the right answer. 1000. 1000. Okay. Therefore, the given circuit acting as a high pass filter, what is the, from which frequencies? Okay, it is allowing from 1000 radians per second onwards, it is allowing all the frequencies to pass through it. Clear everyone? If you have attended my class on filters, you can answer it easily. Okay. Now relate your networks with your analog circuits. Okay. Next question. See the question here. A circuit with an ideal op amp is shown. The Border plot of the magnitude in dB. Okay. And the gain transfer function A of j omega, nothing but V out j omega by V naught by Vi. Also provided omega is the angular frequency. The values of R and C they are asking us to calculate. R and C. What is the value of R? What is the value of C? Do it. What is the value of R? What is the value of C? A circuit with an ideal op amp is shown. Okay. What is the value of R? What is the value of C? They are asking us to calculate here. Tell me. Everyone? Right, here input applied to positive terminal, right? Input applied to positive, and there is a feedback. It is acting, okay, like a non-inverting amplifier, and for a non-inverting amplifier, if you know this voltage here, okay, that voltage into gain. Okay, what is the gain of the inverting amplifier here? Something like 1 plus. Okay, for this one, okay, if you know this voltage here directly, if this is voltage some Vx or V positive, then this output voltage nothing but 1 plus Rf by R1, okay, 1 by R1k into Vx. Okay, right, this is the gain of this one. Yes or no? This is the gain. And here from this diagram, if you notice here, this is given as okay, or simples here at low frequencies. Okay, at low frequencies, capacitor. What is the capacitor at low frequencies? Omega 0, 1 by 0. Okay, 1 by j omega c. It acts as an open circuit. Okay, open. Directly this is a Vn. Okay, open, no current flows, ideal op amp, no drop across this resistor, capacitor opens. Okay, this is the Vn. Okay, gain. Okay, 1 plus, okay, R by 1k into Vx itself. Here the gain, okay, just I am writing the gain. Here at a low frequency I am talking. Since they given the information at low frequencies, impedance of the capacitor. At low frequencies, impedance of the capacitor. Impedance of the capacitor at omega equal to 0, nothing but 1 by 0, nothing but infinity, open circuit. When this is open, this Vin falls here itself, Vin, that Vx itself nothing but at low frequencies Vin. At a low frequency I am talking, okay, low frequency, 0 frequency, okay. And this information they given this gain here 12. At that time this value nothing but V in itself, okay. This V out equal to 1 plus R by 1k into V in. At this low frequency I am talking, at this frequency, gain, okay. Then V out by V in. What is this V out by V in? Okay. This is R by 1k into V in. Then what is this V out by V in? This V out by V in equal to 1 by 1 plus 1k. Okay. We require this information. This is a gain A 1 by R by 1k. Okay. This is a gain. And this is the gain at low frequency. Yes, sir. What is the information they given? 12. Okay. But it is 12 dB. 12 log A base 12 dB. okay, 20 log A, okay, 20 log A, 20 log A, or this is 20 log of, at low frequencies, 1 plus R by 1K. Okay, this value they given as 12, base 10, this is base 10, okay, 20 log, okay, base 10. Okay, then 10, tell me, okay, this 12 how many times? 2 tens, 2 6, okay. This is right now, this is 20 log of 1 plus R by 1K equal to 12. This is base 10, okay, or log of base 10 1 by R by 1K, 12 by 20, nothing but 0.6, 0.6. Okay, or this log when goes to that side, 1 plus R by 1K. Okay, this is nothing but 10 power 0.6. Calculators, take out your calculators, tell me what is the value of 10 power 0.6. 10 power 0.6 here, 3.981. This value is 3.981. I can round off to 4. Okay. Then 1 plus R by 1K. Okay. 1 plus R by 1K. We got 4. Then R by 1K. We get 3. Then R, what is the value of R? 3 kilo ohms. This R equal to 3 kilo ohms. Okay, for the given circuit, they asked to, okay, what is the value of R? Okay, we got this R can be either this one or this one. This is MCQ. One of the options is correct. Okay, you can eliminate these two. You can eliminate these two. Right. Another thing, okay, this information, notice here, this is a 3 dB frequency, 3 dB, 3 dB, okay, and after 3 dB, this magnitude, okay, this is a 3 dB, okay, at which frequency is going here? At omega equal to 3. What information we can get from here? Log of omega base 10 equal to 3 dB, log of omega base 10 equal to, that's a 3 dB. Log of omega base 10 equal to 3 dB. Okay. Then what's the value of omega? Then what's the value of omega here? This omega equal to 10 cube, nothing but 1000 radians per second. 1000 radians per second. 1000 radians per second. Okay. We are talking about these two elements R, this is the C. Okay. And here this is what is the relation between this omega and RC? This 1 by RC. Okay. This 1 by RC we got as 1000. Then what is the R 1K? What is the value of C? This R, I am talking about this R. This R is 1K. And this is C, we need to find here. This is a C. That is 1 by 1K into C. This is nothing but 1000. Or what is the value of C then? 1 by 1K into 1000. Okay, or this is 1 by 10 power 6 or 1 microcoulombs. Sorry, 1 microfarads. Okay, 1 microfarads. Okay, answer here, A is the correct answer. A is the correct answer. That's all, simple question, nothing is there. Right? First find the resistance R from this information. They given the gain, this is a mid-band gain. Okay, from that one gain, substitute no capacitor effect here. Okay, initially. Okay, R we calculated, then we substituted there, right. Next question here. For the following circuit with an ideal op amp, the difference between maximum minimum values of the capacitor voltage VC is dash, they are asking. You do? What's the maximum and minimum? Okay, what is the difference between the maximum and minimum values of the capacitor voltage? Find out, everyone. What is the difference between maximum and minimum voltages? Simple question. This voltage VC. Okay, this voltage VC. And here actually for this circuit there is a positive feedback, right? This output of this stage, okay, fed back here, yes or no? By some network here. Positive feedback is there. Where you have seen positive feedback? Very good, very good. Schmitt trigger. Schmitt trigger circuit. This is similar to a Schmitt trigger circuit only. Okay, positive feedback. But some diodes are given. Okay, based on the output polarity. Okay, you will get that UT upper. Okay, UTP and LTP points. Do it. Okay, I am discussing that point itself right now. Notice here. Okay, everyone, notice here. Notice here. When this output voltage, when it is positive, when this output voltage is positive, okay, means here this side positive, okay, and here like this, like this, like this, this side positive here. Okay, right. Here diode, for this diode, this is a anode, this is a cathode. Notice here, this is a anode side, this is a cathode, sorry, this is anode side, this is cathode side, this is anode side, this is a cathode side. Okay, diode, for diode, okay, anode cathode voltage is more, okay, positive, then this diode will reverse bias. Here anode voltage is positive, okay, this diode will forward bias. Forward bias ideal diode acts as a short circuit. Here nothing told about diode, this acts as a open circuit. Okay, and if you notice this path right now, this is R, this is R, this is R, this is R. Okay, R, 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 and this diode shorted. Okay, diode short circuited, and anything parallel to short, nothing but short itself. This resistance does not have any significance here. This is R, this is R. Okay, right now this resistor does not have any significance. Okay, this resistor does not have any significance. Okay, then notice here, this resistor does not have any significance here, no significance to that resistor, and you have, okay, only this way. Okay, right now this is R, 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 and this is the V out, V out. Okay, this is the V out. Everyone notice here, and this part, okay, given positive, V plus. Okay, that voltage is given to V plus, V plus. Okay, and this voltage is nothing but VC. Okay, virtual grounds that V plus equal to VC itself. This voltage, virtual ground concept. Right now, what is that V plus voltage here? V plus. Okay, if I see this is R, this is R, R, 2R. Okay, right now it seems like this is R, this is 2R. Right now, this two resistors. This is 2R, this is R only, R. Okay, 2R. This is R. Okay, when this voltage is plus 15, okay, plus 15. Okay, can you please tell me what is this V plus? V plus, V plus, I am talking about this voltage, V plus. What is that V plus? Voltage division rule. Okay, this V plus nothing but this resistance R by total resistance, R plus 2R into 15. Okay, this is 15 by 3, 5 volts. 5 volts. Okay, that's nothing but 5 volts. 5 volts. And here this capacitor also charges to 5 volts. V plus equal to 5 volts. V plus, okay, equal to 5 volts. That is when Vc greater than, okay, when Vc greater than 5 volts or V plus, okay, Vc greater than 5 volts, VC, okay, greater than 5 volts. Then this voltage moves from 15 volts to minus 12 volts. A small modification here, sorry. Here in this one, you consider this voltage given as minus 12 volts. Minus 12 volts. That's the data given in the gate. Okay. Then this 15 to that minus 12 volts. It moves from 15 volts to minus 12 volts. 15 volts to minus 12 volts. That point is called UTP point. UTP. This point is called UTP point. Okay. Then that voltage. Okay, it moves from 15 to plus 15 to minus 12 volts. UTP point. Okay, let's move on to next one. When this V out is negative, minus 12, okay, minus 12, I am talking about this value, minus 12 volts. When V out is negative, this side is negative, okay, like this side is negative, this side also negative. Okay, this is anode, this is cathode. Okay, so anode, cathode, this is anode, this is cathode. Anode is negative forward bias, this diode forward bias. Here anode is negative, okay, reverse bias. This diode is reverse bias. Open circuit. Now, anything parallel to short, this resistor does not have any significance right now. Okay, again, how we discussed earlier, this R, this is only one resistor here in this path. And this voltage given to this V plus right now, V plus. And this is grounded, this is R, okay, this is R, and you are getting that, okay, minus 12 volts. Voltage division rule again. Voltage division rule. Tell me voltage division rule here. This is R, this is 2R. Okay, this is minus 12 volts right now, grounded. Okay, tell me this V plus here, V plus. Tell me that V plus. This value equal to 2R by 3R into minus 12. What is value? 2 by 3 into minus 12. This value is minus 4 volts. This is your LTP point. And at this point, it moves from LTP point. Okay. At this point, it moves from minus 12 to 15 volts. LTP point. Okay. At this point, it moves from minus 12 to 15 volts. LTP. And come back to the question, what they asked us to determine. If you come back to this question, for circuit shown with an ideal amp, the difference between the maximum and minimum values of the capacitor voltage, they asking about the capacitor voltage. And right now we found out, okay, we got this voltages V plus, V minus, okay, and try to answer this question. What is the voltage here? 5 volts here, okay, capacitor voltage charged to 5 volts in this case, okay. In this case, capacitor voltage right now minus 4 volts and reached to minus 4 volts, okay. And what is the difference between these two voltages? Okay, 5 volts minus of minus 4 volts. What is the answer? 9 volts is the right answer. 9 volts is the right answer for this question. 9 volts. This 9 volts is the right answer. Okay. In this case, it's this capacitor V plus is 5 volts. This capacitor also charged to 5 volts. In this case, V plus equal to minus 4 volts. This capacitor charged to minus 4 volts. Okay. And they asked us what is the difference between these two. Answer. Okay, right, minus 9 plus 9 volts is the right answer. Next question, MOSFETs. Okay, this also belongs to VLSI or your analog circuits itself. MOSFET, simple question, nothing is there. The circuit shown in figure acts as a linear amplifier. Okay, and VA is the small signal AC input voltage. VA and VB represent the small signal voltage at the nodes A and B respectively. Okay, here for this question they given this as A, okay, this as G. In the question they given VA and VB. Okay, then the values of VA and VB, okay, round off to 1 decimal point. Simple, nothing is there here. Small signal, okay, when you discuss about the small signal DC sources, you have to deactivate the DC sources. Okay, this VG node source, deactivate this source. Okay, this VD, deactivate this DC source, deactivate. Okay, deactivate that one. Okay, replace by short, ideal voltage source replaced by short. Then replace this MOSFET by small signal model. What is a small signal model of a MOSFET? Okay, if you know these terminals of the MOSFET, okay, this terminal, this is a gate terminal, arrow indicated here, this is a source terminal, this is a drain terminal, okay, gate, source, drain. And if I am replacing this MOSFET by small signal model, this is a gate, this is a drain, okay, this is a source. And between drain and source, you have a current source. What is the magnitude of the current source here? Gm into VGS. Gm VGS, where VGS is the voltage between gate and source. VGS is the source terminal. VGS. And suppose if channel length modulation is also taken into account, you will get a R0 resistor here parallel with that current source. And here nothing told, okay, and no information about early voltage. Okay, in BJT we will talk about early voltage. Here no channel length modulation parameter lambda is given here. Neglected channel length modulation lambda. Okay, means no resistance, infinity resistance, R not infinity. Okay, right. This is a small signal model. BJT replaced by small signal model. Next, this is a 4K, this is a 2K, right? 4K, this is a 2K. This is a 4K resistor connected to, okay, like this. Ground. 4K connected to ground, okay, and this voltage nothing but your VA voltage, okay. Next, this is a 2K resistor connected to source, 2K resistor connected to source, and this voltage nothing but your VB voltage, simple, that's all finished. Okay, if I want to do, okay, just for my simplicity, just I am rearranging the circuit here. Okay, see here, same thing, not changing anything, and the input part here, this is open only, and V in does not have any significance here. V in, this is a V in, okay, this is a V in, Vi, okay, leave it. Since they are asking VA, VB only, okay, I am taking this part. This is a Vi, input voltage Vi, and VGS, this voltage nothing but VGS. Okay, and this is your Gm VGS, Gm into VGS, okay, and this resistance nothing but your 4 kilo ohms, and this is your 2 kilo ohms, grounded, this also grounded, okay, and here this is VA. What is this VA, VB? This voltage nothing but VA voltage, this voltage nothing but your VB voltage, VB. That's all, VA, VB. Now tell me everyone, notice here, here this current flowing like this, this is Gm into VGS itself, okay, this also Gm into VGS, this also Gm into VGS, Gm VGS. This voltage is VA with respect to ground, okay. Here this Gm into VGS is flowing like this, Gm VGS, okay, and this VB polarity is plus minus like this, okay. Everyone notice here, okay, Ohm's law, when this current is flowing like this, polarity is plus minus. When this current flowing like this upwards, this polarity plus this polarity minus, okay, simple. Then what is this VB? When VB, tell me this VB polarity is plus here, minus here. This polarity same. VB voltage, if you ask VB, this VB equal to that 2K, Ohm's law, current into resistance, 2K into GM VGS, 2K into GM VGS. Okay. Next VA, this is a VA. VA polarities, if you notice here, this is plus minus. Okay. And when this current flowing like this polarities is plus downwards, minus upwards, or minus plus. Minus plus here, plus minus. Same polarities are reverse polarities. Reverse polarities. Okay. Then what is the value of VB? You ask VB is 4K minus 4K into GM VGS. Minus 4K into GM VGS. That's all. What they asked us to calculate, VA by VB. Okay, do it. Then VA by VB I am writing here. Okay, this is VA by VB. VA, we got VA as minus 4K into GM VGS. What is the VB? 2K into GM VGS. Okay, GM VGS cancel, this value KK cancel, this value is minus 2. VA by VB for the given question nothing but minus 2.0. That's all. Very, very easy question, provided you know the small signal model of MOSFET. That's all. Right, let us move on to next question. A long N-channel MOSFET, channel length L given, okay, channel width is given, electron mobility mu n, oxide capacitance Cox, and their product is given mu n Cox is also given 1 milliampere per volt square. Threshold voltage is given Vt 1 volt. VGS is given as a 2 minus sine 2t, okay, and VDS given 1 volt. What is the, okay, spelling mistake here. Okay, what is the maximum drain to source current? Simple question, nothing is there. Here only you should know the expression for current, that's all. Sir, what is the information given? See here, current expression, maximum drain to source current they told, okay, maximum, okay. If you draw the characteristics of MOSFET, ID versus VDS, IDS, VDS, okay, and MOSFET, characteristics, something like this, something like this, something like this, yes or no? Okay, and this region is called linear region or non-saturation region, okay, this region, non-saturation region, this region is called saturation region. In this saturation region, current will be maximum, okay, they are asking the, what is the current in the saturation region only. And with this VGS, they are asking what is the maximum current also, okay, right. So here, what is the expression for current ID? Actually, ID equal to mu n Cox W by L into VGS minus VT whole square divided by 2. That's the expression for current. Simple, that's all. That's all. Whoever knows this expression, okay, everybody did this question. Whoever knows this expression, simple, nothing is there. Okay, what is the mu n Cox? Mu n Cox they given as 1 milliampere per volt square, okay, this is 1 milli. W by L, what is the W? W given as 100 micro, 100 micro. L value given as 10 micro, okay, this is W they given here 100 micro, L they given as 10 micro, okay, this is nothing but 10 micro, right, divide by 2. VGS minus VT, VGS they given 2 minus sine 2t, okay, minus 1, threshold voltage given as 1, threshold voltage given as 1 whole square. Current equation you can write in a linear region or non-saturation region as well as saturation region. If you consider current equation in saturation, non-saturation region, then you will get VGS minus VT into VDS minus VDS square by 2, okay. But since they ask maximum current, you have to take the saturation region current equation only, okay. And this 10, this is 1 milli into 10 divided by 2 into 1 minus sine 2t whole square. This is your ID. ID. That's all. And here they are asking us to write the maximum current, right? ID maximum. ID maximum. When you will get the ID maxima, see here, this sign value lies between +1 and -1. Sign value lies between +1 and -1. Okay, +1, -1. If I take +1, 1 minus 1, 0. If I take -1, minus of minus will become plus. Okay, consider sin 2t as -1 in order to get the maximum current. This is 1 milli into 10 micro divided by 2 into 1 minus -1 whole square, or this is 1 milli into 10 micro divided by 2, okay, 2 square, or this is nothing but 2 cancel, milli, okay, micro, okay, micro, not micro, okay, this is 10 only. This is 10, okay. What is value here? Tell me. 2 cancel, 20 milliamperes. That's right answer. 20 milliamperes is the right answer. 20 milliamperes. Finished, everyone? Okay, let's move on to next question. Milliamperes. Next, move on to next question. This is the question. Consider the CMOS circuit shown in figure. Okay. Substrates are connected to their respective sources. Okay. Here, this is a MOSFET. For this MOSFET terminal is, this is gate, this is a drain, this is source. In P MOSFET, source always connected to the highest potential, so that charges will move from source to drain, holes will move from source to drain, current also flows from source to drain. The main point is source should always send the carriers, drain should collect the carriers. In N MOSFET, source always connected to the least potential. This is a, okay, and drain at higher potential compared to source. Drain, if electrons flows from drain to source, current flows from, see here, electrons flows from source to drain, current flows from drain to source. That's why source always connected least potential in your N MOSFET. Okay, this is the gate of, right, N. And another point here, by this diagram we can conclude, when drain, see here, this point shorted. Notice here one point, this point shorted. This drain, this gate drain connected same point. So gate and drain are connected to same point, then that MOSFET acts as in saturation region of operation. For this N MOSFET also, this gate and drain connect to same point. Okay, here also this transistor also acts in saturation region of operation. Indirectly they are given from this diagram. MOSFET is operating in saturation region of operation. Saturation region of operation. Okay. From this, okay, what they are asking us to determine here, they given, what is the data given? Threshold voltage, this is -1, and mobility of holes is 40 centimeters per volt second, and N MOSFET threshold voltage is +1, mobility of electrons is 300 square. Steady state output voltage they are asking us to determine. Okay. Okay, right. Here, what is the data we can derive from here? What is the data we can conclude from here? Okay, so here for N MOSFET, for P MOSFET, they given this threshold voltage of P MOSFET as -1 volt here. Mobility of holes, okay, mobility of holes is 40 centimeter square per volt second. 40 centimeter square per volt second. And for N MOSFET, threshold voltage of N MOSFET. For N MOSFET, threshold voltage is +1. And mobility, what is the mobility of these holes? 300 centimeter square. 300 centimeter square per volt second. This is the information they given here. Okay, right. WL ratios also they given here. WL ratios of PMOS is 5. WL ratio of NMOS is 1. Okay, right. Simple thing. Both the transistors are saturation region. Okay. Both the transistors are in saturation region, right? Saturation region. Whatever the current flowing here, same current flows here. Whatever the current here, same current flows here. That's all. Simple, equate the currents. That's all. If you know the current equation, both PMOS and NMOS, we can do it easily. Okay. Current in PMOS, okay, or NMOS equal to current in PMOS. What is the current equation? Saturation region for PMOS, NMOS, mu n Cox W by L by 2 into VGS minus VT whole square. Okay, this is for NMOS transistor. For PMOS transistor, mu P Cox, okay, W by L of PMOS by 2 into VSG minus mod VTP, okay, whole square. This is the current equation for PMOS. And another thing, what they given for both the transistors, Cox is same. That's the information they given. For both the transistors, Cox is same. This is Cox, this is Cox is same. Okay. And here mu n. Tell me what is the mu n here? Mu n for NMOS given as 300. Mu p for PMOS given as 40. Okay. And here connected to the respective gates, the gate width, okay, resistors have the same gate oxide capacitance per unit area, Cox, okay, same gate oxide capacitance per unit area. That information they given. Okay, Cox for both the transistors same, okay, PMOS and NMOS. And this is mu n nothing but 300 centimeter square per volt second. Okay, WL of NMOS is 1 divided by 2. This is VGSN, okay, the VSGP, okay, VGSN minus VTN whole square equal to mu P. What is mu P? 40. What is WL of PMOS? 5 divided by 2 into VSGP minus mod VTP whole square. Okay, right. This two also getting cancelled here. Leave it. Everyone, right. Here, what is the gate voltage of NMOS? This gate connected to drain and gate connected same point. Yes or no? This voltage is V0, therefore this gate voltage is V0. This source connected to ground, okay, source is at 0. VGS of NMOS, if you calculate VGS of NMOS, VG minus VS. This is V0 minus 0, okay, or this is a V0. Okay, V0. Similarly, what is VSG? VSG of PMOS transistor. Okay, this VSG, for this also, this gate connected to the drain. And okay, and since the gate connected to the drain, this is V0, this voltage also V0 itself. And source connected to the 4 volts. Source connected to 4 volts. For PMOS, VSGP. Vs minus Vg, okay, Vs connected to 4, Vg connected to V0. This is 4 minus V0, 4 minus V0, okay. Right now, let us see this one. This is 300, 300 into VGS minus VTN, right? VGS nothing but V naught for NMOS, VT nothing but 1 volt square equal to 40 into 5 into VSG. VSG nothing but 4 minus V naught mod VTP minus 1. Okay, modulus of minus 1, 1. Okay, minus 1 whole square. Or this is 300, 200, the 445 is 200. This is 300 into V naught minus 1 whole square equal to 200 into 3 minus V naught whole square. Okay, 3 by 2. V naught minus 1 whole square equal to 3 minus V naught whole square. Okay, 3 by 2 V naught minus 1 whole square equal to 3 minus V naught whole square. 3 minus V naught whole square. Okay, square root on both sides here. This is 3 by 2 nothing but 1.5 into V naught minus 1 equal to 3 minus V naught. Okay, 3 minus V naught. Let us try to get the expression for V naught here. Let us subtract the terms containing V naught. This is root 1.5. This minus V naught when comes to this side becomes plus 1 equal to 3 minus 1 square root of 1.5 when comes to this side plus 1.5. Therefore, what is the value of V naught then? This V naught equal to 3 plus square root of 1.5 divided by 1 plus square root of 1.5. Calculator, take this calculator and try to calculate this value of V naught. Square root of 1.5, 1.2247. 1.2247 divided by 1 plus 1.2247. Calculator, tell me this value. What is the value of V naught? 1.89899. 1.89899 so and so volts you are getting. So here, if you go to the question, what the question they asked? See the options. Okay, they asked us to the steady state output voltage V naught is. See these options: equal to 0, equal to 2 volts, more than 2 volts, less than 2 volts. They ask. Okay, these are the options given: A, B, C, D. Equal to 0, equal to 2 volts, more than 2 volts, or less than 2 volts. Okay, we got the answer V naught as 1.89899, which is less than 2 volts. Answer D is the right answer. Answer D is the right answer. Okay, done. Everyone. Okay, next question here. This also came from MOSFETs, analog circuits only. Simple expression only. An ideal MOSFET, MOS capacitor. Okay, an ideal MOS capacitor. This is a P-type semiconductor. Okay, P-type semiconductor. This is a P-type semiconductor is given. This is a metal. This side is metal. This is oxide. This is semiconductor. Metal oxide semiconductor. An ideal MOS capacitor, P-type semiconductor is shown in figure. The MOS capacitor is under strong inversion. Okay, strong inversion with Vg 2 volts. The corresponding inversion charge density Qin. Okay, what is the relation between Qin? Okay, Qin and Cox. Simple, Cox into okay Vgs minus Vt. Vt. That's all. Okay. Here assume that oxide gate capacitance okay equal to some value they given Qox they given. So here what they asking us to determine here, okay, what they asking us to determine, they given here Cox. What's the value of Cox given? Cox given as 1.7 into 1.7 microfarad per centimeter square. Okay, that's the value of Cox. Okay, right, for okay, that's a common data given, right. When Vg equal to 2 volts, when Vg equal to 2 volts, what's the Q in inversion charge? 2.2 in micro coulombs per centimeter square. What they are asking us to determine, when Vg equal to 4 volts, what's the value of Q inversion charge? Q inversion charge. That's all. That's the data they're asking. Simple. MOS capacitor, basic MOS capacitor, metal oxide semiconductor. If you know this one, yeah, charge nothing but Cox into VGS minus VT. Whoever knows that relation, they can solve it. That's all. Vg equal to 2 volts. They given this one. Vg equal to 4 volts. They asking. Right? Okay. Right now, tell me. Calculate. Here, whether threshold voltage is given. Okay. First, let us see. Then Vg equal to 2 volts. When Vg equal to 2 volts. Okay. Qin equal to that Qin. Okay. That Qin equal to Cox into VGS minus VT. VTN. Okay. Threshold voltage not given. Let us first of all try to get the threshold voltage with this information. Okay. Threshold voltage not given. Try to get the threshold voltage. Try to get the threshold voltage with this information. Okay. This is VTN. Try to get the threshold voltage with this information here. Okay, everyone, try to get the threshold voltage. VTN or VT. Okay. CQ in given as 2.2 micro. This is 2.2 micro equal to Cox given as 1.7 micro. VGS given as 2 minus VTN. Okay, first of all, try to get that VTN. Micro cancel. 2.2 by 1.7 equal to 2 minus VTN. Therefore, VTN. Calculate this VTN here. VTN equal to 2 minus 2.2 by 1.7. 2.2 by calculator. Calculator. What is this value you got here? This is 1.29411. Okay. 2 minus 1.49. Calculator. 1.29411. So and so. Okay. Therefore, what is the threshold voltage we got here? 0.70589. 0.70589. That's a VT. VTN information we got here. Okay. If you know this VT, now when VGS equal 4 volts, let's substitute. Calculate what are the things they are asking us. VG equal 4 volts. See here, VGS, why I am putting VGS as 2 directly? Vs, this is source connected to ground itself. This VGS equal, Vs equal 0. Vg minus Vs nothing but, okay. Here also Vs equal to 0. Then VGS equal to 4 volts itself. Q inversion charge. Okay. Cox into VGS minus VTN. Okay. Cox given as 1.7 micro. VGS given as 4 minus VTN, we calculated 0.7058 something you take. Okay. Calculator, use it, calculator. 1.7 micro into 4 minus. So 3.29411. 3.29411, multiply it and tell me the answer. What is inversion charge Q in? This is 5.5999. Okay, 5.5999 micro coulombs per centimeter square. That's the answer. Finished. Okay, and they are asking us to determine that value. That's all. Finish here. Simple. Whatever the question they ask from VLSI, straightforward, formula based only. Okay. Easiest questions. Let's move on to next question. Okay, this is came from EDC. What the information they given? In a non-degenerate semiconductor with electron concentration 10 power 16 coulombs. Okay, some N1 they given 10 power 16 per centimeter cube. The difference between bottom of the conduction band and Fermi level of the electron, EC minus EF, they given. EC minus EFN, they given. Okay. This given, they given it as a 200 milli electron volts. for this information. Assume the thermal voltage as Vt equal 26 milli. Vt equal 26 milli, okay, millivolts, milli electron volts, okay. And intrinsic carrier concentration of semiconductor as is 10 power Ni, okay, Ni information also given. This is 10 power 10 per centimeter cube. Okay, if the electron concentration becomes 0.5 electron, okay, it's changed to another value, N2, 10.5 into 10 power 16, okay, per centimeter cube. Then the difference between the bottom of the conduction band and Fermi level, EC minus EF. What is this EC minus EF in for second condition they are asking. This is the information they given for the first condition. That's all. Here also, if you know one relation, we can solve it here. Just a small relation we need to know. Conduction of states, okay, density of states. If you know the density of states, we can solve this. If you know the density of states, we can solve this. What is the density of states? We know N equal to Nc into e power minus Ec minus Ef, okay. Density of states N equal to Nc into e power minus Ec minus Ef by Kt by Q, okay, Kt by Q. This Kt by Q value, okay, this is Vt and this Kt directly given, okay, here the Kt directly given in electron volts. Actually Kt by Q, this threshold Vt, okay, usually value of Vt is nothing but Kt by Q. This value is nothing but 26 millivolts. Right now this Q also charge of the electron also they given like this as a 26 milli electron volts they given. Kt value directly given, Kt. Kt they given as a 26 milli electron volts for this problem, okay, right. And here let us see the data. N1 10 power 16, okay, this N1 equal to 10 power 16 per centimeter cube, okay. This Ec minus Ef, this Ec minus Ef, Ec minus Ef for the first set, okay, Efn, Ec minus Efn for the first set given as 200 milli electron volts, okay. Similarly, here this Vt 26, okay, or that Kt value is 26 milli, Kt 26 milli electron volts they given, and they are asking us to determine N2. For N2, what is N2? For N2 0.5, okay, N2, and N2 equal to 0.5 into 10 power 16, and Ni they given Ni as 10 power 10, 10 power 10 per centimeter cube, okay. They are asking like this, simple here, nothing. Let us try to derive something here, make use of these conditions. Everyone notice here, okay, all right. N1, this N1, okay, N1, if I take N1, tell me N1 equal to Nc into e power minus Ec minus Ef of first condition of first by Kt, okay. Similarly N2, what is N2? N2 equal to Nc, density of state is same Nc, e power minus Ec minus Efn, okay, by 2 by Kt, okay. Then let us take the ratio 1 by 2, okay, N1 by N2. What is N1 by N2? This N1 by N2 nothing but Nc by Nc into e power minus Ec minus Efn of first one divided by Kt, and Nc into e power minus EC minus EF n of the second divided by KT. Okay, here this NC getting cancelled here. Okay, NC getting cancelled. Therefore, this N1 by N2 and e power something by e power something, e power A by e power B, e power A minus B. Okay, we can write like e power EC minus EF n of the second minus EC minus EF of the first divided by KT. Okay, right. And let us substitute this N1 given as 10 power 16, N2 given as 0.5 power 10 power 16. Cancel 1 by 0.5. 1 by 0.5 nothing but this is value nothing but 1 by 0.5, which is nothing but 2. Okay, this is 2. Therefore, this value equal to 2. This value equal to 2. This value equal to 2, right? Okay, then this expression, this 2 equal to e power. What is EC minus EF of the second one? We need to find EC minus EF of the second one. We need to find. First case, this is given as 200 milli divided by KT also. Okay, 26 milli. 26 milli. I will write in a proper way. Okay, this everything e power. E power. Everything is e power equal to 2. Okay, e power when comes to this side becomes a natural log. Yes or no? Therefore, ln of 2 base e equal to this EC minus EFN of second one minus 200 milli electron volts divided by 26 milli. Okay, 26 milli if I multiply here, this EC minus EF of the second EFN of the second minus 200 milli equal to 26 milli into ln of 2 base E. Okay, ln of 2 base E. What is the ln2? What is value? Calculator. ln2, okay, into base 2. This you are getting this calculator, make use of this calculator, you are getting this value as 18. Okay, this value we are getting 18 milli. Therefore, EC minus EFN of the second one nothing but 200 that side going plus 18. Answer 218 milli electron volts is the right answer. 218 milli electron volts is the right answer. Okay. Then answer A, B, C, D. D is the right answer for this question. D is the right answer. Okay, right. One small question. Select the correct statement regarding the semiconductor device. Okay. Mobility of the electron always increases with the temperature, wrong. Okay. Beyond silica 300, wrong. Okay. Electrons or holes have equal density in intrinsic, right? This also MSQ question. Okay. And the total current is specially constant in two-terminal electron device in dark under steady state condition. Very good. Okay. Dark means no light is given, right? No external excitation is given. For collector region is generally more heavier doped compared to base. Very good, right? This also correct only. Here this is emitter, base, collector. Basically emitter is heavily doped, then collector is okay compared to collector, and collector is having high dope compared to base. Okay, just they asked about these two only. Okay, collector is more doping compared to base. This also correct. Okay, this B, C, D all are correct here for this one. Right. One question they asked here, in electrostatic field, the electric displacement density d bar is given as a d bar equal to, where y-axis, x-axis respectively. Okay. Consider a critical region R centered at the origin with each side of the length 1 meter, vertices are plus or minus 0.5. Okay, yeah, this seems like a cube. Okay, this everything is a cube, 0.5 plus or minus 0.5 plus or minus 0.5 cube. Okay. What they are asking us to determine, d bar given, okay, d bar is given, electric charge enclosed. Electric charge enclosed. This question came from electromagnetic fields, EMF. Okay. What is electric charge enclosed? Q enclosed. And we know Gauss law. Okay. Closed surface integral d bar dot ds. It gives the charge enclosed, Q enclosed, or which is also equal to volume integral, okay, del bar dot d bar dv. Do you remember this one? Gauss law. Okay. Since they asked charge enclosed charge, they given the d bar vector. Okay. They are asking us to determine the charge enclosed. D bar, if you know d bar, first find the del dot d bar divergence. First find the del bar dot d bar, del dot d bar. How to find del dot d bar? Dou by dou x, ax cap. Okay, dou by dou x. Okay, of that divergence. Okay, into dot product here. This del nothing but dou by dou x. What is del? Del operator. Okay, dou by dou x, ax cap, dou by dou y, ay cap, dou by dou z, az cap. Okay, this one dot product, this one. Okay, and ax dot, we know one thing, ax dot ax is 1, ay dot ay 1, a dot az dot az also 1. Similarly, ax dot ay 0, 90 degrees apart from each other, cos of angle between them 0, right? Okay, right. Let us calculate that divergence. This is x cube, ax cap. Similarly, dou by dou y, y cube, ay cap, plus dou by dou z. Okay, here, sorry, here you will ax dot ax 1, okay, ax dot ax 1. This is a x cube. Finished. Dou by dou y, y cube. Dou by dou z, x y square. That's all. Okay. This is 3x square. This value is 3y square. This value independent of z, this value is 0. Okay. Therefore, del dot d bar. This del dot d bar you got like 3x square plus 3y square. 3x square plus 3y square. Okay. Charge enclosed. What is the charge enclosed? Charge enclosed nothing but volume integral del bar dot d bar, okay, dv. Okay, this is nothing but volume integral 3x square plus 3y square we got here. 3x square plus 3y square. 3x square plus 3y square dv. What is dv? Cartesian coordinate system dx, dy, dz. And here this x varying from 0.5 to minus 0.5 to 0.5. Y also varying from 0.5 to minus 0.5 to 0.5. Z also varying from minus 0.5 to plus 0.5. Okay. Directly here, see here, and dz, okay, no z term, directly separating z equal to minus 0.5 to 0.5. Okay. Dz, z. Okay. This is surface integral 3x square plus 3y square dx, dy. Okay, x varying from minus 0.5 to 0.5, y varying from minus 0.5 to 0.5. Do it. What is there? Completed. Okay, this value z, substitute the value between 0 minus 0.5 to 0.5. This value becomes 1. 1. And actually 3x square is even function, 3y square is even function, minus 2 plus you can make it twice and make it 0 to 0.5. Okay, and z if I substitute here, this becomes 1. Okay, and this is 2 into double integration, this is 3x square plus 3y square dx dy. Okay, x varying from 0 to 0.5, y varying from 0 to 0.5. Complete this one. Complete that one. Simple integration. Simple integration only. Simple integration only. Complete. Okay, first differentiate with integrate with respect to x. Okay, 3x cube by 3, then 3y square into x, then integrate with respect to y. Okay, substitute those values, you will get 0.5 coulombs. 0.5 coulombs here. Okay, let's move on to next question. A waveguide of two infinite parallel plates. Okay, it's a parallel plate waveguide given like this. It's a parallel plate waveguide. Okay, parallel plate waveguide. And separation between the two parallel plate waveguides mentioned like this. Okay, what is the separation between them? 10 power minus 4. 10 power minus 4 centimeters. A is given as 10 power minus 4 centimeters. Assume the speed of light in air, they given, right? Okay, the frequencies of TM wave which can propagate TM wave. So here the frequencies of TM wave. Okay, here cutoff frequency. What is the expression for cutoff frequency? C by 2A. That's all into M. C by 2A into M. C. Okay, what is the value of C? Okay, 1 second. This is a C M into, okay, 2A M. Actually here this is a question. First calculate the cutoff frequency. Okay, I will give it to you only. Calculate the cutoff frequency. Okay, and above the cutoff frequency, whatever the frequencies are there, all will be passed by this one. Okay, just to calculate the cutoff frequency, all the information is given. TM wave, okay, cutoff frequency. What calculate the cutoff frequency, and all the frequency above the cutoff frequency, it will passes. Simple. Okay, this is also MSQ type question. MSQ, multiple select question. Okay, what are frequencies more than the cutoff frequency, all the frequency will be passed. Just find the cutoff frequency. I am leaving to you. Okay, last question. In a circuit that is a series connection of ideal resistor and ideal capacitor is given. Okay, series connection of ideal resistor, ideal capacitor, RC given. RC, simple. And ideal capacitor, the conduction current through resistor is, okay, series only conduction current they given, J, okay, ID. ID is given as a 2 sine of, okay, T plus pi by 2 given, pi by 2, so many amperes. Then the displacement current they are asking, okay, conduction current they given, conduction current they given, ID, IC. IC they given this way. Displacement current they are asking, ID. What is this? ID they are asking. Simple. ID. Tell me what is ID? Conduction current they given. They are asking us to find the displacement current. Okay. Actually, here some basic thing what you require to know here. JC, conduction current density, nothing but sigma into E. Okay. Displacement current density JD. Okay. Nothing but dou D by dou T. Okay. If you know dou D by dou T, that's all. And this D, how it is related to E? Epsilon E. Epsilon times of E. Okay, this is a dou by dou T, epsilon times of E. Epsilon constant I can remove. I can get it out. Dou E by dou T. Okay, this is a JD. This is the relation between conduction current density and electric field density, displacement current density and electric field intensity. Okay. And here from the first one, I can get this as E equal to Jc by sigma. Okay. And here, if I am substituting in place of E, this is Jc by sigma. Sigma I am taking out, this is nothing but epsilon by sigma dou Jc by dou T. Dou Jc by dou T only. Dou Jc by dou T. That epsilon by sigma nothing but your time constant RC, R into C, that's all. Okay, right, since they given IC, ID, okay, they given IC and ID. See here, what the information we got here, I expressed everything in terms of densities. JD equal to epsilon by sigma into dou Jc by J dou T. Okay, current density, okay, this current per unit area, this is ID by A, okay, this is epsilon by sigma dou by dou T of IC by A. Okay, A is a constant, A is getting cancelled, this ID, okay, this is epsilon by sigma, or epsilon by sigma I can write it as a RC itself directly, RC network IC. Okay, RC network, for RC network this is the time constant R into C, sigma by epsilon, okay, by sigma nothing but this is the ID current, dou by dou T of IC. What is IC given in this question? What is IC given in this question? IC given as 2 sin 2 T plus pi by 2. Okay, differentiate that one, differentiate this one. Okay, actually here sine second quadrant, all silver teacups, sine of T plus pi by 2 nothing but cos T directly. Okay, this is RC dou by dou T of 2 cos T. Okay, 2 cos T. Now this ID equal to 2 times of RC. Okay, differentiation of cos minus sine T. Okay, whether they given options here, whether they given any options here. Okay, maybe options, some options are missing, or you can write 2RC into sine of T plus pi, also you can write T plus pi. This is your current displacement current. Simple, that's all. Displacement current. Hope you have gained some knowledge in this class, okay, by this discussion. Okay, thanks for your patience listening. All the best for your career, everyone. Thank you. Goodbye. Jai Hind. Okay. Everyone.